Hi, my name is Charlie Ziese. I'm the chair of the Pyramid Science Foundation and also the owner of StargatePyramids.com, a manufacturer of personal healing and meditation pyramids. Today's documentary is about finding the golden ratio in fluid dynamics. And before I go any further, I want to allay any concerns that engineers and fluid dynamics professionals may have, because I'm sure you're already asking, well, what does sacred geometry and pyramids have to do with fluid dynamics? Well, that's what this session is really going to be all about. And the short answer to that is that the very geometry that you see in the structure in my background is the exact same geometry that minimizes drag and in any fluid dynamics environment. So that's the reason I discovered uh, this geometry while studying pyramids, but now it's taking me on an amazing journey over the last 6 to 7 years of discovering this in all types of architecture, in ancient buildings, in diagrams, hieroglyphs, uh, and now I found it in fluid dynamics as well. So that's the reason why I'm doing this. I I've turned into a polymath of sorts because the information that I found in pyramids, it has a huge applicability across a broad number of different disciplines. So with that said, I'm going to open up my screen here and we're going to begin to discuss give you an introduction to fluid dynamics and the golden ratio. So here's a picture that shows a few of the many things that we're going to be looking at today. We're going to see this golden ratio scaling angle in so many different environments. Starting at the top left, we're going to see it in fish. On the bottom left, we're going to see it in birds, and then all having to do with their aerodynamic design or hydrodynamic design. Now, in the center here where my cursor is, we're going to be discussing hypersonic vehicles towards the end of the documentary. Bullets, which turn out to be actually one of the prime ways that modern aerodynamics got its start, they all contain this geometry as well. Looking down here, where my cursor is, this ancient diagram, we've got plenty of ancient diagrams that indicate that contrary to what we've been told in our historical narrative from school, we've known about the angles of aerodynamics for a long, long time, and probably had these flying vehicles in past civilizations. We're going to look at a lot of the artifacts that have been left from ancient times and show that these angles uh, show up in these aircraft model designs as well. We'll also look at current day jets. We're going to find that all of the commercial jets, all of the private jets, the fighter jets, and so forth, all contain this geometry as well. To the right here, where my cursor is, this is a rocket engine nozzle. This is actually a nozzle from what's called a ramjet engine. We'll be talking about that as well. And we'll also, going further down, we're going to go back and look at the history of rocketry and see that this geometry of golden ratio scaling shows up in ancient rocketry through the present and into current day hypersonics. And we'll also look at ground-based vehicles, and we'll see all types of racing vehicles where this shows up as well. So we've got lots that we're going to be talking about, and this is a perspective that I can assure you engineers are not taught in school. Despite all of these examples and the many, many more that you're going to see, one thing you're going to find is that if you were to go do a search on the internet for sacred geometry and fluid dynamics or golden ratio and fluid dynamics, nothing will show up. You can go and do as much research as you'd like to in the STEM libraries of major institutions, and you're not going to find anything. So this is all brand new information. It's not brand new because obviously we knew about it years ago when we were starting to develop these, but we've lost this knowledge over time. And we're going to be talking about that topic as well. So to give a brief introduction here, in the ongoing effort to build faster, more fuel-efficient, more maneuverable vehicles and more powerful engines, some of the most fundamental questions posed to design engineers are things like, what's the optimal vehicle design elements that will minimize drag, maintain stability, and maximize thrust? These are key questions for any mechanical engineer in the world of fluid dynamics. Well, one of these design elements is the optimum geometry or angle that will minimize drag. And currently, there is no mathematical formula to accurately estimate this angle. What actually happens is, there's a lot of wind tunnel testing that's done, and you can start with previous ideas and work from them and so forth. But there's no formula, there's no guideline or safe harbor, so to speak. This would be a good place to start. So what this does is it results in lots of wasted time, effort, and money. And as we're going to see, it may actually have impaired the hypersonic program of the United States government. But based on research that I've conducted, a process that I now call Goldden ratio scaling is the answer to this question of what's the right geometry to minimize drag. And based on over 1,000 examples, GRS is the geometric angle that minimizes drag, maintains stability, and maximizes thrust in all types of naturally occurring and man-made objects in both gaseous and liquid environments. Now, Goldden ratio scaling, I discovered it by reverse engineering the geometry of the contemporary Russian pyramids, which used this geometry to produce significant free energy, health, agriculture, and material science benefits. Having read the research when I was first introduced to these pyramids 8 years ago was really the motivator for all of this subsequent research. But from that starting point, I was able, once I re-engineered or reverse engineered this geometry, I was able to find Goldden ratio scaling in all sorts of ancient diagrams, free energy projects, ancient architecture, hieroglyphs, religious architecture, all around the world. Now, nature confirms that this architecture, wasn't just to make things look pretty. GRS is found in the anatomy of all of the fastest fish and birds, for example, in nature. And it's also found in some fundamental processes in nature, such as the refraction of light through a glass sphere, the amplification of sound, tornado funnels, water vortexes, and it's even found in our DNA. So it's obviously a very, very significant geometric angle. Contemporary wind tunnel testing is not the original source of knowledge of Goldden ratio scaling. This knowledge has actually been around for thousands of years, and we're going to see that it's found in ancient aeronautics artifacts, books, and drawings. Nazi German scientists advanced rocketry and aeronautics before and during World War II. Perhaps the best known result of their efforts, the V-2 rocket, demonstrated a very advanced level of aerodynamics and rocket thrust maximization. This knowledge has been carried forward into the current era by the Nazi scientists who ultimately came to work both in the United States and the Soviet Union after World War II to develop each of these countries' respective space programs. Both the US and the Soviet Union developed numerous experimental aircraft, spacecraft nozzles, and other types of hypersonic vehicles using Goldden ratio scaling during the 50s through the 70s, which was a time of great expansion of knowledge in aeronautics and speed. And they all ended up using golden ratio scaling in their designs, as we'll see. When the new hypersonic age began in the early 2000s, Russia continued to incorporate GRS into their hypersonic technology, and this resulted in the successful deployment of a number of hypersonic weapons, including the Avangard, which has been successfully tested at Mach 27, the fastest vehicle speed ever recorded. Now, according to public available blueprints, however, the United States decided to use a different geometry than GRS when it designed its HTV-2 hypersonic glide vehicles. These vehicles were flown in test flights in 2011, and they disintegrated due to high temperature buildup, which is likely due, at least in part, to the geometry used. And you'll come to appreciate that after you see that all of these other designs up until that time used golden ratio scaling. So fascinating, and it's subject for discussion later on. So based on available internet data, the geometry of U.S. hypersonic glide vehicles still do not conform to the successful GRS geometry used in hypersonic weapons developed in Russia, China, India, and Iran. Now, I'm not trying to start a conspiracy here or anything, but this is the best available data that we have, and it's fascinating when we get there to see that for some reason we changed the geometry, and it seems to have negatively impacted the results that we've achieved. So why is this information important? Well, obviously, in fluid dynamics, finding the optimal angle for reducing drag, it would be a great benefit and save enormous amounts of time and design costs, but also allow engineers and CFD professionals to devote their efforts to other important aspects of vehicle design. For example, as time goes on, you're going to see that conical designs that used this geometry were slightly modified to become more bell-shaped. So there's different subtleties that you're going to find that need to be improved upon as well. But if we could settle upon, and test to verify that this is the optimal angle, we could pretty much set that as a given and start to test other variables and cut down on the amount of wasted effort and motion. In nuclear fusion, a number of companies are using implosion concepts and technology to attempt to achieve nuclear fusion. And as recently as a couple of years ago, we had a number of different companies who were able to achieve fusion, but no one has been able to achieve fusion at an over unity point. What does that mean? Over unity simply means that the amount of energy that's taken out of the system or generated by the system is greater than the amount that it takes to produce it. So right now we have the technology to create fusion reactions. It just takes more energy to do it right now than it would take than the energy that we get out. So by applying the proper geometry, which this could theoretically be, since it's so omnipresent, that may actually have a significant impact on achieving over unity results. And then finally, in the world of cosmology, the omnipresence of golden ratio scaling lends significant credence to the principles found in Plato's quadrivium, namely that the universe and all things in it are created pursuant to very precise laws based on the interplay of mathematics, geometry, and harmonics. And the research also tends to verify the ideas that Johannes Kepler had centuries ago, and others, that the nesting of the Platonic solids may in some way be intimately involved in the process of creation, as GRS conforms precisely to the geometry of the nested platonic solids, as well as to the geometry of the scaling of fractals. So very profound stuff here. We're starting to find that these old ideas of the nesting of the platonic solids and the scaling of fractals, and they all end up corresponding with this very geometry that we're now finding literally in the fabric of the ether. So why hasn't this information been discovered before? Well, obviously it has been. Otherwise, these ancient buildings and the ancient aeronautic designs wouldn't have had these geometric angles in them. So sacred geometry, however, has not been taught as a formal area of study for the past 500 years. In the early 16th century, the quadrivium, an advanced body of study attributed to Plato, stopped being taught. And this knowledge explores the interplay of mathematics, geometry, and harmonics in the creation of our physical experience. And the 16th century was also the time that Gothic cathedrals stopped being constructed. And my prior research in other areas has demonstrated that all of the steeples in the Gothic cathedrals contain exponential powers of the Goldden ratio in their geometry. So the builders of those ancient cathedrals had a very sophisticated knowledge of the Goldden ratio. But what's interesting is that none of the major Christian church owners of these cathedrals, the Roman Catholics, the Lutherans, Church of England, I'm sure there are other churches that own a few of these, but those are the major ones. They don't have any publicly available documentation on the sacred geometry found in their steeples. And that's fascinating to me. How did that happen? So it looks as though this information was lost about 500 years ago. The angles that were used, as we're going to find as we go through the history of aeronautics, they continued to survive past the Middle Ages. But a lot of times maybe the underlying theory behind it has been lost. So it's very interesting that these angles continue to show up without any knowledge of the engineering community as to their origins. And then finally, in our increasingly specialized world, holistic and integrative thinking has really been eschewed by academic orthodoxy in favor of specialization. And that's important because I'm having to take a holistic perspective. I have to learn about sacred geometry and pyramids and free energy and all of these different things. So I would be considered to be, a polymath in the world of traditional science today. And that's not the thinking that prevails in the scientific establishment today. And typical of this point of view is the words of Neil deGrasse Tyson, who states that probably only 1 in 10,000 heterodox people have a point. Well, I'm one of those 10,000, and I hope by the end of this documentary that you'll realize that I do have something that I think is relevant and very important for people to understand. So now let's get on to who's going to be interested in this. Lots of different people are going to be interested in this information. Mechanical engineers, computational fluid dynamics professionals, sacred geometers, implosion and free energy physicists. We're going to see some free energy applications in this as well. Certainly hypersonic engine and vehicle design engineers, as well as nuclear fusion physicists and people like me, polymaths. So let's go through and see what we're going to be talking about. The documentary is divided into sections and subsections, and we've got a timestamp in the comments section here, so you can follow that. A lot of you are not going to want to listen to all of this information. So, or if you want to listen to it out of order, that's perfectly okay as well. But I wanted to tell you about each of these sections, and then you can use your own judgment as to how you want to proceed going through the information. But part one is an introduction to the Goldden ratio and Goldden ratio scaling. Tells you how I came up with this, where I found it, how I was able to decipher what Goldden ratio scaling is. Part two, Goldden ratio scaling and naturally occurring phenomena. You're going to see this in light refraction and sound and in the wind and so many other uh, naturally occurring phenomena. And I think that's important for all of us to understand that without even man-made or fluid dynamics examples, we see this geometry in these phenomena, and we have to question, isn't this or is this actually built into the fabric of the universe? Part three, Goldden ratio scaling in ancient architecture. Here I'm going to be showing you examples of ancient architecture from, throughout thousands of years, all different cultures, religious traditions, and the like. And you're going to see how omnipresent this geometry is in ancient architecture. And then part four is going to show you the same thing in ancient artifacts like hieroglyphs and drawings and the like. And so you're going to see there that, this has been known as well for thousands of years. Part five is a model of Goldden ratio scaling. I mentioned earlier that the platonic solids scale in this geometry as well as fractals. And so what I've done, I've developed a model of Goldden ratio scaling. It incorporates the torus, it incorporates the Fibonacci series, it incorporates fractals and the platonic solids. So that's going to give you a theoretical basis and show you that this ancient knowledge that we've discarded for some reason actually seems to be reflective of what observations we found in the world of fluid dynamics. And then finally, in part six, we get into fluid dynamics itself, and I'll just go through this list. We'll look at this Goldden ratio scaling in water-borne animals and birds, ancient aeronautics, in post-quadrivium aerodynamics, in maritime vessels, in racing vehicles. And in that group, we're going to see soapbox derby cars, 40s and 50s concept cars, sports cars, Indy cars, Formula One cars, dragsters, bullet trains, land speed record vehicles. Then we're going to move into Goldden ratio scaling in munitions, in lighter than air vehicles, paper airplanes, helicopters, private jets, commercial jets, supersonic aircraft, airfoils as well. That's the structure of the plane wing and helicopter wings and so forth. So then we're going to look at it in the angle of attack of airplanes and helicopters. We're going to look at vortex generators, Vortilons. Then we're going to start looking in the world's fastest aircraft, in spacecraft, in missiles, engine nozzles, both jet and rocket engines, and ramjet and scramjet engines. And then we're going to look at the GRS and experimental aircraft that were developed not only today, but back in the 50, 60, 70 timeframe when speed was key. And then we're going to see it finally in hypersonic vehicles. We'll look at a case and then look at a case study of the DARPA HTV-2 geometry versus that of the Avangard. In the appendix, I put together many additional examples that we're not going to go through in the main part of the documentary. Examples of tornadoes, water vortexes, iron furnaces, maritime vessels, helicopters, private jets, commercial jets, supersonic aircraft, and missiles. And most of these are very complete. I didn't want to put all this in the main presentation, but for example, commercial jets, I've looked at every commercial jet and every commercial jet plane that's been made since World War II is included in that summary. Same thing with private jets. Maritime vessels, I have every military plane and submarine that's been manufactured since World War II. So a very, very complete list. So I appreciate your taking the time to look at this. I hope that you're going to find this to be of interest and value. And when we come back, we'll begin. Part 1, Introduction to the Goldden Ratio and Goldden Ratio Scaling. Researchers Nassim Haramein and Dan Winter have demonstrated that the universe and all things within it are scaled using the Goldden Ratio, or phi. However, neither researcher identified the process by which this was done or the associated geometry required to accomplish this. Over the past 8 years, I've been researching the factors that affect pyramid energy fields, and the Goldden Ratio, as it turns out, is absolutely essential to their function. This research has led me to develop a model of how the Goldden Ratio manifests within the geometry of the Russian pyramids, which are a series of contemporary pyramids constructed and researched through funding from the Russian government. As the publication of this research, which is by far the most extensive research ever performed on pyramids, was censored by the West, I had to reverse engineer this geometry of the Russian pyramids and found that the geometry links to a process that I now call Goldden Ratio scaling. Now, evidence of the Goldden Ratio scaling is hiding in plain sight in nature, as well as in architecture, ancient symbols, hieroglyphs, free energy devices, sacred geometry diagrams, and ancient aerodynamic artifacts, proving that the ancients were well aware of and used Goldden Ratio scaling. My discoveries, therefore, are nothing more than a rediscovery of this documentation and this knowledge that's been around for thousands of years. Now, what is sacred geometry? This is a challenging question for many people, even those of us who do this consistently. But sacred geometry describes the fundamental laws which create everything in our existence. These laws unite consciousness and matter, as well as science and spirituality. One of the primary tenets of sacred geometry is that geometry, mathematics, harmonics, and proportion are all directly involved in the miracle of creation. The ancient study of this interplay is found in the quadrivium, an advanced system of learning that was attributed to Plato. Teaching of the quadrivium, however, was halted about 500 years ago at the end of what we call the Middle Ages. And it also coincides with the time that the Gothic cathedrals stopped being built. Now, what is the Goldden Ratio, or phi? The Goldden Ratio is the ratio of a line segment cut into two pieces of different lengths, such that the ratio of the whole segment to that of the longer segment is equal to the ratio of the longer segment to the shorter segment. Now, this is an equivalency, but it's really not an equation. There's no way for you to calculate this except through trial and error to find it out. And what we find is that the Goldden Ratio, which is the solution, is an approximate number of 1.618033 ... You see it there on the page. Now, that is an irrational fraction, which means that it goes on forever and it cannot be computed precisely. However, as we'll see, it conforms perfectly to the needs of a model that I put together to describe and depict Goldden ratio scaling. So anyway, the Goldden ratio, as a result of its unique properties, is nature's natural scaling ratio. Now, what is Goldden ratio scaling? There's two gentlemen, maybe more, that have done this. Nassim Haramein, his information is on the left diagram, and Dan Winters is on the right. And they both demonstrated that the universe and all things within it, from the galactic down to the subatomic, are scaled with the Goldden ratio. And so their research demonstrates the universe uses a very precise methodology for organizing matter and information that's based on this Goldden ratio. Although neither researcher devised a model depicting how this occurs, my research has led to the development of a model that does just that. So here's a picture of Nassim Haramein in the movie Thrive, which came out, I don't know, about 12 to 15 years ago. He's with Foster Gamble in this particular portion of the movie, and you see here a holographic image of the torus, and they're discussing that. So the other end, and here's a picture, by the way, of a perfectly circular torus. We're going to be getting into this quite a bit more later in the documentary. But as you see, a perfectly circular torus is going to have horns within it that conform to this very geometry that we're going to be discussing today. So keep that in mind. The other major researcher in this area is Dan Winters. Dan has been perhaps the greatest advocate of implosion-free energy since the time of Victor Schauberger, and certainly is the leading contemporary proponent of that theory. And he's written two books, one entitled Implosion, and his more recent book is called Plunk Fire, which describes these processes in greater detail. Now we'll move on to the Goldden ratio and the Fibonacci sequence. The Fibonacci sequence is a recursive formula. Many of you have probably heard of it, but in mathematical terms, x sub n is equal to xn minus 2 plus xn minus 1. So in mathematics, if we start with using 0 and 1 as the first two numbers in this sequence, we can calculate the Fibonacci sequence to be 0 and 1. The third number would be the sum of the two previous ones, or 1. Then the next number 2 would be the sum of the two previous, which would be 2. And 3 is the sum of 1 and 2, and so forth. So you see how that pattern results. So this is called the Fibonacci sequence. It's perhaps one of the most famous sequences in mathematics. Now, in order to find the Goldden ratio with the Fibonacci sequence, the next thing we need to do is to divide each number in the series. We're going to exclude 1 because you can't divide by 0. But if you start with the second and third numbers, you can divide each number in the series by the preceding number and get a relationship or a ratio. Thus, the first ratio is 1 over 1 is equal to 1. Now, if you look at the chart up at the top of the page, two things to show you. First, you see phi here, 1.618 dot, 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 is on this, would be on that axis there in that line. So you can see that the first step in this process, this chart depicts it. We can plot 1 as the first result. Then if we take 2 and divide by 1, we get 2, and we plot that up here. We can continue this process. We can take the third set of numbers, 3 divided by 2. That's going to be equal to 1.5. The fourth is 1.666, and it continues on ad infinitum. Now, a couple of things that you'll notice, we started out quite a ways away from the actual or a precise definition of phi, in these relationships, but very, very rapidly, it alternates between being below and above the actual phi number, but it rapidly approaches this number. Now, this is called a recursive formula, and what we're finding is an asymptote. An asymptote or asymptotic function is something that you can approach with a continuous repetition of a recursive formula, but you'll never be able to get it precisely. And that's exactly what happens with the Goldden ratio. So the key thing to see here is that this process, if taken to infinity, we could arrive at a perfectly precise calculation of the Goldden ratio. Now, I want to get into Goldden ratio scaling in the Russian pyramids. And why is that important? I make these and sell them in my business, Stargate Pyramids, and this is the way I got started learning about Goldden ratio scaling about 8 years ago. So we're going to see on the left here is a picture of one of the pyramids that was built by the Russian government in Russia. And I have measured what's called the slant angle of that pyramid to be 76.345 degrees. Now, the next one over is just an example of the pyramids that I make for sale. And in the center was actually one of my very early logos because I knew that this torsion energy, this spiraling torsion field, was occurring inside the confines of this pyramid. So how did I figure this out? I knew from information provided by Dr. Goldden, who was the lead researcher on the Russian pyramid research, that the Goldden ratio was involved in the construction of the Russian pyramids. But I knew that there were no two-dimensional kind of relationships like a ratio of height to base length that would give me any sort of a Goldden ratio relationship, because I knew that no two-dimensional relationships of that nature existed that would come up with this angle. So what I decided to do, I came up with an idea. I knew that in classical cosmology that all creation is thought to occur from the sphere. Well, it was easier to actually model that in 2 dimensions. So if you look at the model that, or the diagram that I'm pointing to now, what I did was I came up with some circles and decided to stack them on top of each other. I started with the bottom circle with a diameter of 1. And what I did in each case, I divided the previous diameter by the Goldden ratio. So when I divide 1 by 1.618 ... I'm going to get the next diameter of 0.618. I divide that by 1.618. I get 0.382, 236, and so forth. Now that continues on to infinity. You will never reach the top of that triangle in 2 dimensions or that pyramid in 3 dimensions, but it will allow us to determine some angles and relationships by constructing the sides of the triangle in 2 dimensions, and then we can expand that into 3 dimensions later. But what we come up with as a result of that, you can see on the right-hand column, is an angle at the base, which is called the slant angle, of 76.345 degrees, and we get what's called an apex angle at the top of 27.309 degrees. So these are going to be important to remember, but that's the methodology that I used. And it wasn't long before I started to find confirmation of what I had just accomplished. And where did that come from? But lo and behold, another pyramid. As it turns out, the Giza pyramid in Egypt, which I have plotted in this along with the Russian pyramid, has some striking phi relationship, Goldden ratio relationships that concur with the geometry that I had developed for the Russian pyramids. And so we can go over those very quickly. The height of the Russian pyramid which would be points DC here. That's 4.116, whereas the height of the Giza pyramid is 1.272, are the square root of phi. Now, the Russian pyramid is 2 times the square root of phi cubed, which gets pretty complex, but the ratio here is 2 phi. So there is a phi, not only is phi found in both of those heights, but the relationship between those is also a phi relationship as well. Now, the slant height, and we're going to be talking about the slant height much more so than the height of these pyramids going forward. But the slant height of the Russian pyramid is 4.236, or phi cubed, and that's from point CF. And point EF, the slant height of the Giza pyramid, is 1.618, or phi. So they all have phi in their geometries, and that ratio is phi squared. Now, the last relationship here is probably the most crucial, because what I found was that the slant height of the Russian pyramid at 76.345 degrees is exactly equal to the apex angle of the Russian pyramid. Now, we're not going to get into this in this documentary, but in my other documentaries, I go into some depth as to why and how that occurs. So now I want to talk briefly about phi convergence and Goldden ratio scaling. Now, we talked about phi convergence just a minute ago with that chart with the Fibonacci sequence. So what I want to point out is that some researchers in this field have the impression that the Fibonacci series will only produce this effect of phi convergence using an initial number pair of either 0 and 1, or alternatively 1 and 1. But in fact, any two initial numbers other than 0 and 0 can be used with the Fibonacci sequence to achieve phi convergence. Now, this is an extremely important point, as it points to the fact that the Fibonacci sequence works as a perfect model to depict and define Goldden ratio scaling. We'll be getting into that a little bit more later. Now I want to just talk briefly about the angles that we're going to be talking about today that are associated with Goldden ratio scaling, and there are 3 of them. The first one is 76.345 degrees. You saw this picture earlier. This is essentially the base geometry of any triangular or conical object that meets at a point higher up, and that angle in Goldden ratio scaling is 76.345 degrees. Now, the other angle that's important is the apex angle, and that is depicted here. This is actually the one of the steeples on the Ulm Cathedral in Germany, and it's 27.309 degrees. And this is the angle of things like nose cones on rockets and airplanes, missiles, nozzles, and so forth. And we're going to be seeing that a lot today. And in fact, that's the one that we're going to be using the most, if for no other reason, it's the easiest to measure in most of these situations. And then finally, the third angle that we want to talk about is 13.654 degrees. And that happens to be 1/2 of the 27.309 degrees that we just talked about. Now, this angle appears in situations where the geometry on the bottom of the vehicle, if we were to model that like a cone, it would create an unwanted turbulence and or flutter. And that would be harmful to the design of the vehicle. Now, you'll see this in situations where the intake of a supersonic or hypersonic vehicle is involved, or in land-based vehicles such as race cars, world record land speed vehicles, and so forth, where scaling that on the bottom of the plane of the vehicle would actually produce a tremendous amount of flutter, and therefore, couldn't is not a wanted outcome. Now, Victor Schauberger, a researcher from the 20th century that we'll be talking about later, he used this very seashell that we see below here to develop Goldden ratio scaling, and it was the inspiration for some of his free energy devices. So, here is at least one example of 20th century free energy technology that we know already has used this geometry and this very same approach that I'm bringing to light for his inventions as well. Now, on the bottom here, I'm showing a supersonic transport plane, and I'm doing it so that you can see the front of a supersonic plane has this 13654 geometry in its nose cone. And the reason for that, if you point through to the arrow, you see this appendage on the bottom of this airplane. That's actually where the engines are. We're used to seeing them mounted above the wings or on the wings or immediately under the wings in a traditional commercial aircraft. But in a supersonic and hypersonic type environment, you're going to see those engines actually placed below the body of the craft, and that's the reason you don't want to be, pushing air down underneath, because it's going to cause turbulence in the flow of air into the engine. So that's the reason we're going to see this 13654 angle as well. Now, before we leave this section, I want to go back and just explain how do we get 76,345 and 27,309 again. We saw that 76,345 on the bottom, and actually in a two-dimensional context where this is easiest to understand, you can multiply or add 76,345 to 76,345, and then if you subtract that from 180, which is the sum of the angles in a triangle, you're going to get that 27,309 remainder, and that's the way the math works on the geometry. Before we finish section 1, there's also one other important topic that I want to discuss, and that's explosion and implosion. Explosion is characterized by the sudden and forceful liberation of immense energy, resulting in a profound disruption of the surrounding environment. And this release of stored potential generates a rapid expansion of gases and the violent expulsion of particles in all directions. Now, virtually all of mankind's contemporary energy technologies are based on explosion. We're going to be discussing the exceptions to those rules a little bit later. But most of this explosion technology we can see manifested from anything from internal combustion engines to TNT to nuclear fission, for example, and rocket and scramjet engine nozzles. So we're going to find this in a variety of different places. Now, I want to go over so you can get a little bit better understanding of explosion, and then we're going to talk about implosion. But I want to first focus on the bottom left diagram. Now, that's a simple explosion there, it looks like, in 2 dimensions. Now, you could perceive that, if you're like me, you might also perceive that diagram as occurring at the top of a cone, in the interior of a cone. Now, that's what I'm trying to depict in part in the diagram immediately above it. What I've done is I've taken the geometry, the 2-dimensional geometry of the Russian pyramid, and I've shown 2 situations that occur in real life. One, you can see the arrows of air that meet the point, the tip of the object as it's moving through space, and you can see that the air is having to conform to the outer dimensions of that geometry. And we can deem that as explosion. Now, as a real-life example, let's look over at the diagram immediately to its right. This is Russia's Avangard hypersonic missile. And sure enough, it maintains this very same geometry of Goldden ratio scaling. And so what those outside arrows are trying to depict is the flow of air that occurs when that Avangard missile flies through the air, and it has to to move and conform to the geometry of the object that's moving through space, in this case, the missile. Now, another example and idea that you can get from this comes from, and we're going to be talking about these a lot more later too, rocket nozzles. These happen to be some rocket nozzles from Russia, but what they depict is, again, the exact same geometry is being used to maximize thrust. And in that situation, it's very similar to thinking of an explosion here at the top or the tip of this two-dimensional triangle, which is a two-dimensional representation of the pyramid or a cone. So those are important concepts. Explosion occurs both on the outside and it can occur on the inside as well. Now let's go through and discuss implosion. Now, implosion is a phenomenon where a structure or an entity succumbs to inward collapse. This is alien to many, many people, so stick with it. This occurs when the equilibrium between internal and external pressures is disrupted, leading to a rapid and profound convergence towards the center. Now, implosion is the energetic process used by Victor Schauberger. We mentioned him before. The Russian pyramids that I have researched extensively. It occurs in jet airplane nozzles and many other free energy inventors and inventions in the development of their technologies. Implosion can also be found in contemporary examples such as Ramjet and Scramjet engines, all of which we'll be describing. Nuclear fusion technologies are also using implosion and could potentially benefit enormously from the knowledge and use of this precise geometry. So now let's go back and look once again at these diagrams. Here we have an implosion, and we can see that the energy is being coalesced. And again, in that if you think about this in 3 dimensions, you can kind of see that energy and matter is being compressed at the top of this cone, which is exactly what I've tried to depict with the diagram that I've put together below. And again, this is essentially the way that the Russian pyramids or any pyramid is acting. It's taking the torsion fields that are coming up from the earth and they're consolidating, combining them, and that is, with the right geometry, is causing implosion inside that geometric form. Now, similarly, if air is moving up, you can see if it's not directly underneath the triangle or cone, then it's still, there's going to be a low pressure area, in effect, that is created, and the energy fields are naturally going to want to come in together and coalesce along the sides of the geometric shape. Now, an example of that is the egret, which I have a picture of here below, and we'll show again later in the presentation. In this situation, we see that the bird constructs its dive in such a way that its wings make this very 76 345 degree angle as it's diving to catch its prey. So what, again, is happening here, there's a low pressure area that is developed behind the body, and the air is going to come back and fill up that vacuum or low pressure area. And it's going to move with this very geometry, because we're going to find this is the geometry that minimizes drag, maximizes speed, improves fuel efficiency, and the like. So essentially, one of the key things to see here is that implosion and explosion are really just sort of like mirror images of the very same phenomenon, because it's really just a question of the direction of flow as to whether we have implosion or explosion, but the geometry remains absolutely the same. Part 2, Golden ratio scaling and natural phenomenon. In this brief section, what I'm going to do is to show you how golden ratio scaling shows up in our world around us. And the first example I want to demonstrate is the refraction of light. This particular experiment was done by a researcher named Clay Taylor. And what he did was to take a pipe which was open on one end and was sourced by sunlight. And on the other, so sunlight is streaming through this black pipe, and on the other end, they put a glass sphere at the end of the pipe and measured the angles of refraction that came through the glass sphere. And sure enough, what turns out is that this geometric angle seems to perfectly match that of the refraction of light. So seemingly what this is demonstrating, one example, that the refraction of light demonstrates kind of a baked in or cooked in geometric angle through which light will refract. So this is an example of explosion that we just discussed, where the light is expanding out from its original source with this angle. Now here's another example. This is sound amplification. On the left, we have the megaphone, which those of us who are a little older know from football games. Although this has been supplanted to a large degree by electronic megaphones in the contemporary era, we use this very geometry to amplify sound in the past. And another example of that I remembered from childhood, I looked up recently, and that's the Victrola record player, which I remembered from childhood. It was a little before my time, but the logo of RCA Victor, which is shown on the right, is called His Master's Voice, had the Victrola record player on it with this very geometry. And as you can see, it was used to amplify the sound that came from the stylus needle running across the tracks of the record. So this is another example of implosion. And interestingly, or explosion, and here's an example of sound with implosion. This is an old, early hearing aid device, which used, again, the same concepts to bring the sound together and to allow them to be amplified in early versions of a hearing aid. Thank goodness we don't have to go through this anymore, but it's another example of this fundamental geometry showing up in natural phenomena. Here's another example that has to do with the air and wind, and these are racing sails for racing sailboats, and you can see at least at the bottom of each of these, there's a slightly different geometry or configuration to these sails, but the one on the left, it was easier to see it just on the bottom of the sail, but you see it on this example on the right, from top to bottom on this particular sail as well. So very, very close to this geometry. Here's a couple more examples of racing sails with this geometric angle. And here's some other examples of this geometry seen in the air. It's very hard to find an example of a Dutch windmill that would allow me to measure this angle, but I was able to find this photo, and it certainly looks like the 27,309 angle is extremely close to the angle of the windmill blades on this Dutch windmill. And on the right, similarly, this is an old style of a farm windmill that was available, I think, in the Midwest. Certainly it was in Texas where I grew up. And these were used to help bring water, from wells up to watering holes, literally for cattle and other animals around the farms and so forth and ranches. So another example of this geometry in the air. And here's another example. This is a ceiling fan in my home, actually. Rather than the 27309, we see the 13.645 degree geometry. And I think that's in large part due to the fact that we, in this case, we have a ceiling that, is impacting the flow of the air. So we're seeing a different angle in that situation. Moving on to a totally different kind of phenomenon, that's tornadoes. I did an extensive study of tornadoes a while back, and I found, at least 50 examples of fully formed tornado funnels which had this geometric angle as well, indicating that there's something about this geometry that allows it to form in situations where there is a tremendous amount of energy being put into the system. Now, I'm going to show you a few more here of tornadoes, but I have many more examples of these tornadoes in the appendix. But one reason why you may not necessarily see this all the time is because you find this phenomenon, this geometry, only when the tornado is essentially, somewhere between its organizing stage there in stage 2, step 2, and its mature stage in step 3. But beforehand and afterwards, you're not going to see that. But again, what this is demonstrating is nature uses this geometry to form energy into this swirling vortex, which of course is characteristic of what we're going to be seeing in other examples later on. So tornadoes are yet another example of this geometry in nature. Similarly, when you look at water vortexes, you find the very same geometric angles showing up. Here's an example, several examples that I took. Again, I have many, many examples, more in the appendix, and certainly more that I have in my own personal portfolio, but you'll get the idea here. Now, it's only when you find a situation such as this example where there is maximum amount of energy input into the system that you can see how perfectly this geometry shows up in the context of a vortex. This is a high-speed machine that was producing this water vortex, and we can see the angles are very, very precise, indicative that this system has kind of reached a full energy component and shows off this geometry perfectly. And here's another example I just wanted to show of seashells. These are just beautiful, structures, but they also show the spiraling of the vortex that is, this is representing in each of these three cases. So we'll be talking about a lot more examples in nature in future sections, but you can see that nature knows this geometry. It's cooked in to the very fabric of the design of these seashells. And lastly, for this section, I wanted to point out that our DNA has this geometry as well. On the left side, I attempted to measure to the very best of my ability, and you can see I came up with an angle that seems to indicate the 76-345 geometry showing up in the geometry of the DNA. On the right-hand side, we see the Goldden ratio much more clearly in one revolution of the DNA, and you can see how it's split into the greater and lesser pieces of the DNA and we see the Goldden ratio relationship. So we've seen now this in 3D phenomenon in a number of natural phenomena, and so we can see that nature uses this. It's embedded. It's literally in the fabric of so many natural phenomena. So in coming sections, we're going to be looking obviously at other things such as architecture, and then, of course, ultimately into the world of fluid dynamics. Part 3, Goldden ratio scaling in ancient architecture. In this section, we're going to be showing examples of Goldden ratio scaling in ancient architecture from all cultures, all religious traditions. And it demonstrates again that this geometry was very, very well known and used for a long, long time in architecture. We're going to start to explore the potential use of this geometry in the case of free energy in these ancient architectural drawings as well. So we're going to be studying other facets such as artifacts and ancient aerodynamics and other sections. But let's begin. On the left is a church steeple from the Ulm Cathedral in Germany. It's the tallest cathedral in the world. And you can see this particular steeple here has the 76-345 geometry on it, as does the one on the right, which is a mosque in Samarra, Iraq. So we're going to be studying these examples and many more in this section. So we're going to start with some ancient structures that are found in the island of Sardinia in Italy. This is an island in the Mediterranean, large island, and it is part of the country of Italy. Now, these structures are called nuraghes, and they are found throughout the island. People are not totally sure what their original purpose was, but every one of these structures, and there were originally over 20,000 of these. There's about 7,000 that are, at least partially or completely still intact on the island. But these, the bases, at least, of these structures have been dated by certain methodologies to go back as far as 300 to 350,000 years. Pretty hard to imagine. However, these structures are all, you can go inside, you can get inside of these. They're conical in nature, and we're not sure exactly what their purpose was. However, as we're going to see, stone structures with this geometric angle have been found elsewhere in Africa with significant ionization fields in them, and we'll be talking about why that's important. But one of the most important factors to know is that this is highly subjective, but when you go to the island, you automatically feel a very, very high energy field here, number one, which could be caused by these. And also the island is what's called a blue zone, which means that it's one of the healthiest places on the planet to live, because longevity on the island of Sardinia is among the very highest to be found on planet Earth. So moving on, that's not the only place where we find these kinds of conical structures. There are a variety of brocks that can be found in Scotland. Again, ancient conical structures. This is the best preserved. This is called the Musa Brock in Scotland, but there are, literally hundreds of ruins of this type that we can find in Scotland. And these date back, according to archaeologists, to sometime in the first millennium BC. So they're not quite as old, apparently, as the ones in Sardinia, but we find these as well. Here's one that that's been studied to a large degree by two researchers. One is Michael Tellinger, who is from South Africa, and also Dr. Sam Osmanagic of um, Bosnian pyramid fame. So this is the Great Zimbabwe ruins, which are in current day Zimbabwe. This ancient structure, as you can see on the left, was it looks like it was kind of an enclosed, a fortress of some sort. But enclosed inside of it is this ancient conical structure we're seeing once again with this very same geometry. Now, why this is important is because several years ago, um, Dr. Sam and Michael Tellinger measured the level of ionization in this particular ruin and found it was literally off the charts. It was higher than any other type of ruin that they had ever measured before. Now, why this is important, and we're going to be talking about this a couple more times, is that there's research done by the University of London that the presence of high levels of ionization in the atmosphere reduce viral load by over 90%. I believe it was 99% was their findings. So if you're in the presence of these energy fields, as I am with my pyramids, you find that you don't get sick anymore. So this all is just kind of correlating, coming together. But once again, we're seeing this geometry in yet another culture, and they were using this for some purpose that we're still not sure of, but it produces these amazing benefits of health through the process of ionization. Here's another example. Many castles around the world uh, are structured with this geometry. And some people may suggest, and it is possible, that this geometry is used because it provides stability for the foundation of the and the structural integrity of the castle itself. But what I'm going to argue is that unlike the caricature that's on the right, where this was used as some sort of a fortress of some sort, which I highly doubt, this could have been some sort of a square wave transmitter or receiver, but no matter what it is, that we're finding this geometry yet again, and this is not the only castle. There are numerous castles around the world, uh, which I would actually call forts, just to distinguish them from castles that one lived in the past, but they all contain this geometry. Now we're moving on into India. Um, all of the Hindu temples have this geometric angle as well. And we're not going to dwell a lot on ancient Indian architecture, except to say that there are two major styles, and they both use this geometry. This is called the Nagara style or Northern Indian style. And what's important about these, besides the fact that they contain the GSR geometry in their structure, is the fact that they also demonstrate a sophisticated knowledge of fractals. And what we're going to find later in the discussion here is that fractals scale with this very same geometry as well. So there's a lot to learn from these ancient Indian temples. And moving on, though, to another style of Hindu temple. This is called the Dravidian or Southern Indian style. And this is the Thiruvannamalai temple in India. Now, on the top left, we're going to start to see a lot of what researchers call antiquitech. This particular temple, a researcher in India named Praveen Mohan, that's the gentleman in the top left-hand piece of the slide here, has done a number of excellent research videos on Hindu, Buddhist temples of all sorts in that part of the world. And he did one in particular on the Thiruvannamalai temple. One of the things that he talked about was the fact that there is inscribed, as you can see in that top left-hand corner, what looks to be a Tesla coil that's buried underground and seems to work as an energy device of some sort. And what Praveen tells us is that at the bottom of this temple, the lingam comes out of the ground, and the room in which it kind of appears has a very high temperature. I think the normal temperature is over 100 degrees, even though a structure like this should keep the bottom of the temple quite cool. So there's clearly some energy devices that were being used that are probably no longer working in this temple. So his presumption is that this temple and many other temples in that part of the world were originally power plants of some sort. And as further evidence of that, I've blown up on the right-hand side the top of the largest temple in the complex. And what you can see at top of it is the ancient, these balls that Praveen has stated, contain mercury. And in the presence of uh, electromagnetic fields, the existence of mercury in these balls, the mercury can be force or will spin as a result of being in the presence of an electromagnetic field. So this is an example of antiquitech that many people have theorized was used in the production of ancient electricity, and seeing the lingam Tesla coil as well adds much more credence to this fact. Here's another temple. This is a Buddhist temple called the Mahabodhi Buddhist Temple in Bodh Gaya, India. And once again, we're going to see the GSR, excuse me, the GRS geometry here, not only in the body of the temple itself, but also in the coil that exists at the top of this structure. So once again, we're being this lends itself to some sort of energy production and or harvesting that's being done with these temples. Now here's another geometry of temple with this 76-345 geometry at the top of it. This is a hemispherical structure, and although these are now deemed to be religious buildings, one can easily see that this could potentially, as we're going to look at Tartarian architecture, this could be some sort of a resonance chamber that was used to pick up certain Earth energies and to have them resonate within this. But again, fascinating that these ancient buildings all contain this geometry in their structure. Here's a pagoda in China, the Great Wild Goose Pagoda that has this geometric angle in its structure as well. And here's an example of a synagogue that's in Kaliningrad, Russia. This used to be Königsberg, Germany, prior to World War II, and after World War II, this area became part of Russia. But you can see on the left, there's an old synagogue here, and we're going to see these increasingly. We're going to talk about these balls, just as we saw in the Thiruvannamalai temple. You're going to see these kinds of balls that likely contained mercury and may have been some part of an energy harvesting electrical generation process. On the right, we see this synagogue was destroyed during the bombings in World War II, but it was rebuilt more recently, and it's maintained the same geometric configuration as before. Here's the Great Mosque of Samarra that we talked about before, that's in Iraq. And it's interesting that the spiral staircase going up has this very geometry as well, and conforms to the direction of torsion field flow that's theorized to exist in our world. What's fascinating is this next photo. This is a depiction of the Tower of Babel Babel, Babylonia, Iraq. Yes, it's all the same territory from the past. And we see this temple of Samarra here. And interestingly enough, this depiction of the Tower of Babel seems to have this 76.345 degree geometry in it. What's more important is that I have an entire chapter that demonstrates that painters of this uh, Tower of Babel depiction have used this same geometric angle in all of the depictions of the Tower of Babel, which makes me think that there's something hidden beneath the surface here, both in terms of perhaps biblical history and our own history that needs to be examined further. Here's another example. There are a number of what are called stav churches in Norway. There are a couple of replicas of these in the United States, up in the upper Midwest, Minnesota and South Dakota, that are also in existence. But these were built from about the 9th through the 11th century, and then they abruptly stopped being built. But they all contain this geometry in their steeples as well. Now, here's another example of wooden churches that were built in another part of Europe. This is in Romania. There's a section of Romania that borders Hungary and portions of Ukraine where we find these churches were built as well. As you can see, it's a little hard to see, but there's some lines that are coming down from the an antenna that's atop this, which could be reflective of free energy technology, ion harvesting, which we're going to talk about here in just a minute. Now, here is an example of a Gothic cathedral. This is the Naumburg Cathedral in Germany. We previously saw the Ulm Cathedral at the beginning of this section. And once again, this is the geometry that shows up. And what's more important from a free energy perspective is to see these iron balls. We see there's antennas of some sort at the top of these steeples. But more importantly, this structure of having a larger steeple with these 4 smaller steeples surrounding it seems to be a common characteristic. I don't know how that worked in terms of free energy, but once again, we're seeing all of these characteristics of antiquitech in Gothic cathedral steeples. And although this is an aside, this is research that I did last year. The geometry in the third one, which is 27309, that's the Goldden ratio scaling that we're discussing today. But what I was able to decipher was the fact that every one of the Gothic cathedral steeples, and this continues into current day times in our contemporary office buildings, will find these exponential powers of phi in the geometry of every Gothic cathedral steeple. And as I say, it's been carried on into present time. And interestingly enough, the churches today don't even know that this geometry exists. Neither the Lutheran Church, the Church of England, Roman Catholic Church, they all own large numbers of these Gothic cathedrals, but there's no information available on the sacred geometry of these steeples. But it does exist, and that tells us that it's not an accident that all of these other structures that we've seen have had this geometry. I'm not going to go into this, but this is just an example how I was able to figure that out. There are the Giza pyramid and the Russian pyramid geometries I already knew, and when I found these and kind of categorized them, I saw that there was an intermediate angle and then 3 that were steeper. And what I was able to do was to figure out the apex angles, which I can measure with an online protractor app to determine if they fit or don't fit within the structure of these 6 geometries. And I measured over 500 of these, and they all fit perfectly. Another place where this is found is in ancient castles. And we're going to see here, this is a Königsberg Castle in Germany. Once again, we're seeing the 76-345 geometry with the ball up there, with some sort of an antenna on top, and the four smaller steeples or spires underneath it. And this is characteristic of every castle. Every castle that I looked at, and that's hundreds of them, they all have this very same geometry. And it's important to know we have these large structures, and researchers of these castles have indicated that uh, there were no electrical facilities. There was no way to heat or cool these facilities, and that many people believe that there was some sort of ion harvesting, electrical harvesting that was being done using geometry as the driver to make these ion fields. And here's another example of a castle that's in Belgium. And here we can see once again, this one is very similar to the Thiruvanni temple in India in the sense that it's rectangular in nature, but it maintains its geometry. And we can see up here again all of these types of antennas on top in an era when we supposedly didn't have communication and or electricity. Now, all of this brings up an interesting topic. I've been looking to try to replicate what I believe is this ancient ability to create ionization. We're going to be talking about that again here in a few minutes. And what I found when I started doing research is a company online which I think is of interest to should be to a number of people. It's called the Ion Power Group. They have begun the process of recreating an ion harvesting, and it's a startup company. But what they have been able to do is to create a nanofiber carbon material, which is able to collect ions in the atmosphere. Now, the basic way that this works is that as you get higher into the atmosphere, there's a greater number of ions in the atmosphere, and what it looks like these ancient art buildings, such as the castles and temples, were able to do was to collect that energy and to transfer it into some other usable form of energy. Now, what they have done, this nanofiber ion collector is able to be put up into the sky and to collect ions. And as the further you go up, the more effect you have of this. And essentially, what you're doing is to establish an electrical potential between the sky and the earth, and by so doing, you're able to actually create free energy. Now, they're and that's depicted here in the diagram on the left. Now, what I'm showing on the right here are examples of the antiquitech that you can find throughout the world on these ancient buildings. We keep seeing on the top right hand here with my cursor, you many times see these balls, which I believe contain mercury, but you're also seeing the existence of fractal antennas. And what researchers on the internet have demonstrated is that crosses, stars of David, and even crescents, which are the symbols of the three major Abrahamic religions, all contain or can be used as fractal antennas. So it seems as though these are just different ways of potentially achieving the same results that Ion Power Group is getting with their nanofiber. But it doesn't matter what the technology is. The driver, apparently, of why we're able to see these ionization fields is, in fact, the geometry that's contained in Goldden ratio scaling. Now, another example of this is in the bottom right hand. You can see in the top right-hand corner, we've got both the cross and the crescent. In the bottom left-hand corner, we see highly fractalized antennas atop some churches in Russia, which are all part of some Tartarian architecture that we're going to talk about in just a minute. So that's another potential form. You can see wires coming down also from the top right-hand corner, and these may have been used again to harvest. Another technique is shown in the cathedral steeple in the bottom right-hand corner. People have depicted or assumed that these were some sort of capacitor structure that was able to gather energy as well. So there seems to be evidence that that was in fact what was done. Another area of ancient architecture are ancient bell towers. This is the San Marco bell tower in Venice, Italy. The same geometry at the top. They knew that this angle was going to help to magnify the sounds from the bell tower. And once again, I'm just showing you we've continued that knowledge, that technology into current times as demonstrated by the geometry of the megaphone. Another place where we find this geometry in ancient architecture are obelisks. All of the obelisks that are attributed to having come from Egypt have this 76-345 geometry. So they knew about it, they used it, and we're not sure yet. Many people theorize that this was also part of a free energy technology. So we'll just keep that in mind as we proceed on. Now we're going to go over to some architecture in Russia. This is a corner arsenal tower in the Kremlin complex in Moscow. And as you can see, this is picture on the right. It has this geometry, as do almost all of the towers there. And as you can see, each of these towers with this geometry, this is pre-Edison era. So this is not apparently this electricity was not produced through traditional electrical means. But this is just one example of many of pre-Edison illumination. There's many in Paris that I have in the collection we're not going to see today, but towers with this 76-345 geometry are depicted as being the source of free energy illumination. And finally, to finish up this section, we're going to just look at St. Basil's Cathedral in Moscow. This is actually part of the Kremlin. It was originally a cathedral. When the Soviets took over, it was subsumed and became part of the Kremlin and was a museum, although more recently, regular church services have now begun to be held again inside the cathedral. But here we see so much antiquitech. We have these onion dome structures, which we're not going to talk about, but I think because they have the same types of antiquitech, the crosses, and most importantly, we can see, at least in the right photo, you can see that there are electrical lines coming down from the top of the cross and going down possibly into the ground, that this could all have been part of a grand free energy structure. So in the next section, we're going to start to look at this geometry and some ancient artifacts, but this concludes the section on ancient architecture. Part 4, Golden Ratio Scaling and Ancient Artifacts. We're going to go in this section, we're going to see a number of ancient artifacts, symbols, diagrams, just a smattering of the examples that I have to give you an idea that this was recorded for posterity in a number of different ways. And the first one we're going to look at is the Lesser Key of Solomon. This is an ancient kind of symbol and diagram that has this golden ratio scaling geometry right there for us to see. Geometer George Leoniak has actually taken a drawing that he's put together of this geometry, and he's done an overlay of it to demonstrate that. So we're going to be seeing this diagram a little bit later, but it's a classic example of the type of symbology that incorporates this geometric angle. Now, here's a classic example of the caduceus. The caduceus is actually, the universal symbol for healthcare around the world. And what's fascinating to see is that the geometry of the snakes, or the coil that symbolizes, that's coming, that's in this symbol, demonstrates this very geometry once again. So hiding in plain sight. And it's fascinating because I know the health experience that I've had with the pyramids. I don't get sick anymore. It's hiding in plain sight. Here's another one. Now we're moving on to Egypt. This is the Temple of Karnak hieroglyphs from Egypt. You can see the Russian pyramid geometry here in this hieroglyph. Interestingly, it seems as though it's always paired with the Ankh, which is to the left, which is another major power symbol from ancient Egyptian hieroglyphs. So this geometry was clearly, known about in ancient Egypt, and we'll see some later depictions of this in a few minutes. Here's an overlay of the hieroglyph, and what we've got here is an overlay that George Leoniak has done, which demonstrates. I had always wondered what the smaller cutout pyramid was supposed to represent. We're going to talk about this scaling geometry diagram that George has put together later, but essentially what we're seeing here is that when you use what are called golden ratio circles, which George has done here to amplify each of these and scale them, you can see that this phi cubed scaling geometry seems to fit, and that the border here seems to represent the difference between one scaling dimension and the next, and then we can see how it fits perfectly in that smaller pyramidal structure that we have on the outside. So this diagram seems to have a lot of information attached to it, demonstrating this golden ratio scaling. And here's another major ancient diagram. This one's from India. This is called the Sri Yantra. It's depicted there on the left. And on the right, George Leoniak from New Geometry, again, has done this for me. What he's done, Patrick Flanagan developed a system of drawing the Sri Yantra a number of years ago. And what George discovered was that when you do the first step of that process, which is to draw the Giza pyramid, which you see here in red, inside of a circle, the horizontal line of the Giza pyramid is going to be slightly below the center point of the circle in which it's circumscribed. So when you do that, what you find is that the 76.345 degree geometry shows up as part of that whole process. So embedded in the Sri Yantra is the 76.345 degree angle. Now, for those of you unfamiliar with the Sri Yantra, it's essentially, many people feel, and I do too, that it's actually a two-dimensional depiction of a three-dimensional object, which, when drawn in 3 dimensions, looks very much like a pyramid. Here's another example of this in the Aztec calendar. I had noticed years ago that the geometry of the pyramids that show up in the calendar had this geometry, but George has taken this to its next level and has demonstrated that these phi spheres, golden ratio spheres that, or circles that he's drawn here correspond perfectly with the Aztec calendar. So there's a lot of sacred geometry that's in the Aztec calendar that results from golden ratio scaling and depicting that with this overlay. And here's another one that George found. It's this one was very difficult. He's been doing this for a number of years, and it was only after we started collaborating that he was able to find this. And but it's not in any sacred geometry, textbooks or anything that have these kinds of diagrams in them. So this is from Georg von Welling. It's called Le Grand Mystery. And this was done about 300 years ago, a little bit after the 16th century, obviously, but the golden ratio circles, again, perfectly line up with this diagram. And we can see this scaling geometry inside this diagram, hiding in plain sight. And then moving away from those and into some headwear diagrams that I think is important for us to see, even in Western culture, more contemporary. Medieval witch and wizard hats had this 76-345 geometry, and since they were actually the inspiration for the dunce cap, it has it as well, as we see on the right. The story here is that a 13th century Franciscan priest named John Duns Scotus started experimenting with witch and wizard hats and found that he was able to connect to his higher self or to God much more easily. And so he started advocating this for people to use as a way of connecting directly with God. And the Catholic Church didn't like that. They started vilifying his work. And that's why, even though it originally had the intention of improving consciousness and raising consciousness, it was ultimately, vilified and became an object of scorn and ridicule for young children who didn't do well in school. They had to wear the dunce cap. So fascinating how history has changed the original intent of that cap. And then finally, this is just one example. There are numerous examples of ancient Indian Hindu deities, male and female, wearing ornamental headwear, such as this worn by the female deity Meenakshi in the Hindu religion. And this depiction, as I say, can be found for virtually all of the deities as well as the male deities as well. So fascinating to see how this geometry has permeated diagrams and even our headwear that we're unaware of today. Part 5, a model of golden ratio scaling. While I was exploring golden ratio scaling in nature and architecture, it became apparent to me that there were other observable scaling principles that could, in fact, mathematically and geometrically correlate with golden ratio scaling. And so before we begin to actually see golden ratio scaling in fluid dynamics, which is going to start in the very next section, I wanted to develop this model because it's important to know that nature uses the golden ratio. We're going to see that in other contexts, and we kind of accept it, but we've never figured out how the golden ratio is used in three-dimensional scaling. So what we're going to look at in this model, we're going to answer a number of questions. Some of those questions that arose when I was, involved in this research were the following. Are there any relationships between golden ratio scaling and fractal scaling? Because fractals scale too. So, do they scale at the same rate? Are they correlated in some way? It seemed like an important question to figure out. Second one, are there mathematical formulas that can actually model Goldden ratio scaling? Because, it's one thing to see it and perceive it, but there has to be some sort of a model, mathematical way of accomplishing Goldden ratio scaling in order for us to believe that it could be used in nature. The next question, can Goldden ratio scaling be linked with the torus? So we've discussed all creation in classical cosmology is assumed to start in a sphere. So, could we link the torus with the Goldden ratio scaling? And then finally, are there any relationships between Goldden ratio scaling and the nesting or scaling of the platonic solids? Again, another one of these classic ideas from antiquity that we've sort of tossed aside in contemporary society. Well, as it turns out, the model that I've developed answers all of these questions in the affirmative. So what we're going to see here is that Goldden ratio scaling will scale fractals, it scales platonic solids, and it conforms within the torus. So we've got lots of information to cover here, so let's get started. So here's just a quick summary of the major components of Goldden ratio scaling. The model is composed of the following major components. What's the Goldden ratio scaling formula? Well, we've seen that already. We've seen that the Fibonacci sequence with those, recursive successive divisions by the previous values, using those formulas we used earlier, provides what appears to be actually the only viable method for formularizing GRS, but it works perfectly. Then the next thing I found was that fractals, in fact, scale at with this very same geometry and scaling rate, as do the platonic solids. And finally, the torus horn geometry that's found in a circular torus have this very same geometric angle as well. So what we're going to see is that each one of these components is a part of this model and helps to explain how the universe scales fractals through the use of the platonic solids in the torus. So just to review, we've known for a long time, and I'm sure a lot of you have seen these examples. These are examples of 1- and 2-dimensional Goldden ratio scaling. And so in the left, we have a picture of the human body. This is an example of Goldden ratio scaling in the human body. And you can see it's all done in one direction here. It's from top to bottom in one dimension. So that's an example of finding, the Goldden ratio in scaling in one dimension. Now, on the right-hand side, we have a sunflower, and I'm sure all of you can see that there are spirals going in both directions that are Goldden ratio spirals. And so we can see the magnificent creation of Goldden ratio scaling in 2 dimensions in the sunflower. But what very few researchers have done, I think I'm probably the first and certainly the one who's done it the most, is to look at this in 3 dimensions and to put a model together to demonstrate how it works. So the first thing I want to talk about is the Goldden ratio scaling formula itself, which is using the Fibonacci sequence and then dividing each successive number pair by the number by the previous number in a recursive fashion. And so what the results we're going to see are going to demonstrate are that any 2 number pair values in use of the Fibonacci sequence other than 0 and 0 can be used to achieve phi convergence, and that the sequences that occur can be scaled both larger and smaller, ascending and descending scaling, with perfect precision using this formula. And that's a fundamental requirement for the success of any scaling methodology. So what I've done on this page to demonstrate how this model works is to look at the ascending and descending values using 4 different examples. So on this page, we have ascending phi convergence using 4 different initial values. So if we go to the yellow section, this one starts with the classic 0 and 1 that we've seen in the Fibonacci sequence. So that's the first number and second number, and I've used the same methodology here for 3 other scenarios. But you'll see here the progression that we're used to seeing 0, 1, 1, 2, 3, 5, 8, 13, 21, and so forth. And what we can see is how quickly the Goldden ratio uh, or this process approximates the Goldden ratio. So we see that the first iteration is 1, then 2, 1.5, 1.66, and it keeps going. It becomes increasingly precise as we go along. And by the end of 24 iterations, we have phi down to 8 significant digits. Now, in the second, that's the classic example. But what I want to show in the other 3 is the fact that you can take any 2 number pairs and this will work. So I took the number 1 and the number 1 billion in the second example. And with what's fascinating, if you look at the yellow and this example, with the exception of the very first result, the precision is exactly the same in both cases to 8 significant digits. Now, this is indicating that there's so much more that we need to study here with vortex mathematics. And I'm sure that what we're going to find is that we'll be able to find a very precise model based on numbers alone that will provide the information for developing the Goldden ratio scaling. In the third example, we have 500 and -50. And as you see, we have the same level of precision. When we get down to the last example, we're significant down to 8 significant digits. And then finally, in the fourth example, I have 2 negative numbers. I started with -50 and -10, and we end up with exactly the same result. So I'm not sure, I'm not enough of a mathematician to figure out how to formally prove this, but I hope that this shows you that this is going to work under any circumstances, at least for ascending scaling. Now, on the next page, I want to show you how these same numbers work in descending scaling. And so what I've done, I've reversed the process, and now rather than adding these 2 numbers, I'm subtracting them from each other. And in each case, for example, the first case, I have 46,368 and 28,657, which are actually the last 2 numbers that we came up with in this scale on the ascending side. And so now instead of adding those 2 together, I'm subtracting them, and we'll see that our 8 significant digit precision starts to fall away, unlike in the ascending situation, but it comes down and ultimately results in the exact same numbers that we had in the ascending example. So it scales on an ascending and descending basis exactly the same. And the same thing holds true for these other 3 examples. We end up in exactly the same place that we started. So that's an important concept, the Fibonacci sequence, even though this part of it has been hidden from us or undiscovered. I'm sure it was discovered before, but we haven't known this. So the Fibonacci sequence provides that scaling formula to make this model work. And just to show you briefly how that would work, this is an idealized scaling. I've already assumed that we're at, a highly significant level of precision here, but I've just taken an example where I started with a diameter of 3.077. And when you divide that by 5, you get 1.902. But that was done in such a way that we can add these two or subtract these two together from each other, and 3.077 minus 1.902 gives us a result of 11715 for a diameter. So we can, we can essentially see that these two will create the third one in red. And then essentially in that process, the first one is no longer involved in the process, but we now have the second and third that will produce the fourth, and so forth as we go along in this infinite progression of Fibonacci scaling. So now that we've seen that model, I'm going to show you some other reasons why this is this information is highly significant. For those of you who are familiar with this, we're still going to review this for a second, but I've used vortex-based mathematics to accomplish some information that I want to show you here in a minute, but I want to explain what that is first. Vortex mathematics, or vortex-based mathematics, is a relatively recent field of mathematics that has garnered considerable attention due to its supposed association with Nikola Tesla, particularly his fondness for the numbers 3, 6, and 9. And its creator, Marco Rodin, posits that this unconventional mathematical approach uncovers the fabric of the universe. And we're going to see that there's a lot of truth to what Marco was saying in the next couple slides. So the foundation of vortex mathematics lies in the belief that certain numerical patterns provide insight into physical reality's inherent energy patterns. So with that said, I want to show you, these are a couple of the classic diagrams associated with vortex mathematics. You may have seen these before, but this is a diagram that Marco uses to describe how vortex mathematics works, how certain patterns can be derived from that. And this is an example of a torus which is mapped with this very vortex mathematics system. So just to give you that background. One of the things that's important and about the Fibonacci sequence is that it produces unique fractalized number sets. Now, what do I mean by that? This is the original number set that we saw before, starting with 0 and 1, and what you can see is that it doesn't really matter where you start in this process. I've used in the sidebar there the numbers 610 and 371. They show up in the middle here. If you have those two numbers and you apply the Fibonacci sequence, you can scale ascending or descending. It doesn't matter where you start, but it's essentially all the essence of the number set and its fractalization is inherent in any two number pairs that you take out of this sequence. So once you have those two pieces of information, you have all the information that you need to set up the scaling, golden ratio scaling with respect to those numbers. So to go back to what Marco was talking about before, one of the things that I did to see the impact of vortex mathematics on what I had just determined with the Fibonacci sequence, I found out that every initial number pair that we can possibly come up with when reduced to base 9 is going to fit within one of these repeating number patterns when reduced to base 9 vortex mathematics. Now, to explain that, if you haven't done if you haven't done vortex mathematics before, I'll explain it very simply. It's kind of, some people call it casting out of nines or reduction, but if you have the number 13, you add 1 and 3 together, and that reduces in base 9 to 4. If you have the number 20, you add 2 and 0, and you get the number 2, and that's the reduction. So essentially, any number pair will reduce to one of 9 initial numbers in the 1 to 9 Vortex math series, and the same thing is true for the second number pair. So since there are 9 possibilities for the first number and 9 for the second, you have 81 number pairs essentially reduced to base 9. And what you find is that when you do that reduction, every one of these is going to fit into one of these number pairs. So we've got 3 strings here of 24 numbers, which seem to be random, but if we start with the first one as an example, we could start at the very end here, and we'll see a 1 and another 1. If we circle back to the beginning, that's the first 2 numbers without the 0 in the classic Fibonacci sequence that we're all used to seeing, and then it continues on 3, 5, 8, and what would be 13 when reduced to base 9 becomes a 4. So you can see how that pattern works. And there are other patterns that show up here as well. And additional patterns include situations where you're dealing with number pairs that reduce to 3s and 6s. They can show up as manifest in various arrangements of 3s, 6s, and 9s. And finally, if both numbers are reduced to base 9, both the first and second number pair, then you're going to have a string of all 9. So yes, indeed, when we think of things in this way and you see that the patterns that develop, you see that the world is infinitely mathematical and geometric in nature. So we see now that we have a formula that will, which is the Fibonacci sequence, which will confirm and conform each of these patterns into a repeating pattern in base 9 vortex mathematics. Now I want to go on to fractals. As we said earlier, fractals scale with this very same phi cubed scaling rate. And where I found this came from Richard Merrick's book, Interference. For those interested, you can go to interferencetheory.com, and there are free copies of this book. It's an outstanding source of information on harmonics and sacred geometry. So a good read, but heavy in math, but it's an excellent read. And I've read it 3 times, and I still need to read it some more. But one of the key things that I learned from this book was that this is an example of fractals called the Mandelbrot set. This is the most famous depiction of fractals, I assume, that's out there. But what Richard demonstrates is that each of these circles diameters end up increasing by phi cubed. So we're finding this phi cubed relationship going on yet again in fractals. So you see this very tiny dot here near my cursor, that's phi. Then the next one is phi cubed. This one is scaled phi to the 6th. And then if you draw this out in a circle, you end up with phi to the 9th as well. So it looks as though fractals scale with this geometry as well. So just another fascinating correlation, because the model essentially incorporates fractal scaling at the same time. Now I want to talk about Goldden ratio scaling in the Platonic solids. Mystery school teachings have long held that the Platonic solids play a fundamental role in creation. It's theorized that the 5 Platonic solids nest inside of each other in a scaling pathway that's inextricably linked to the formation of our physical reality. That information has left our mainstream education hundreds of years ago, but you still find information about it if you search hard enough for it. And the following pages actually demonstrate that this scaling process can only occur within the Golden ratio scaling geometry. So we're gonna take a look at that as well. And this is a profound validation, in my view, that this ancient system of knowledge and these beliefs are further validated, and that it validates the teachings of the ancient quadrivium. So before we start to look at that, I just want to say that this is not pure theory. There's been research done with microclusters, which are an intermediate state between the ether and solid matter. And in a particular experiment, they took 460, excuse me, gold atoms and drop them into a tube and watch them form. And what happens is they change form and morph back and forth between these 5 platonic solids, just as it's been theorized, for centuries. So there's a real reason to believe that there's some validity to this thinking. I first became aware of platonic solid scaling when I was reading Robert Lawler's book, Sacred Geometry, Philosophy, and Practice. And we're going to look at a diagram that's on the very last page of that book, which is shown on the left. Now, what this is, it's a diagram of all of the platonic solids. Not every one of the 5 are drawn in that diagram, although these what are called the circumscribing circles and spheres that would encapsulate these, are there for us to measure and observe and to study. So the diagram itself shows the side radius and the sizes of these circumscribing circles, such that we can derive the geometry and the scaling geometry that's involved with each of these platonic solids. So again, the theory is that you can, sort of like keys on the piano keyboard, although there's 12 to an octave here, if we consider one cycle through here as an octave, we've only got 5 keys, major keys. And those are the icosahedron, octahedron, tetrahedron, cube, and dodecahedron. Now, what I've done in the Excel spreadsheet that you can see in the center of the page, I've taken the side links that are in this diagram, and I have determined through calculations in a book on sacred geometry and platonic solid angles and lengths, I was able to determine the ratio of the radius to the side, and therefore determine the radius of each of these as they progress through. And that gave me the ability to determine the diameter of the circles that inscribe each of these figures. And so what we find out, if we start with the smallest icosahedron in this diagram, its diameter is of the circle is 0.7266. And we can go through and check the diameter of the circumscribing, circles in 2 dimensions, spheres in 3. And what we find is that there's basically only 3 major steps, the one in yellow, blue, and green. 3 of these steps occur within essentially the same circumscribing sphere. But the bottom line is that the icosahedron sphere and its radius, when we do the math, is exactly 4.236 times, or phi cubed, times the radius or diameter of the previous octave. So once again, we've been able to prove that this phi cube geometry that we've discovered in nature and in architecture is showing up in the platonic solid scaling. I don't believe that that's an accident. Can't be. Now, this is a diagram from geometer George Leoniak, and it just shows the progression of how each of these platonic solid forms will morph and change, get bigger. And what he's demonstrated here, just using the dodecahedron as an example, that from one octave to the next, the dodecahedron increases in size by phi cubed. And finally, here's an example. George has not used the dodecahedron, but a very close relative to it, which is the rhombic tricotahedron. And what he's demonstrated is that if you take the geometry that the phi scaling geometry, and you interpose that into the tricotahedron, you're going to find that it's a perfect fit. Part of the circle, sticks outside and kind of is the link to the next, scaling geometry. This goes on infinitely, as you may know. So this is just more, confirmation that this ancient sacred geometry and this Goldden ratio scaling geometry fits perfectly within the spherical torus. This is another example from George that shows how the scaling of the platonic solids works. He's drawn a diagram here, and this is the diagram we saw when we were looking at the hieroglyph from Egypt. But he's showing how the geometry of the pyramid, relates to the scaling of the platonic solids. He's used the cube as his reference point, at least for the scalings. But this diagram he has in GeoGebra, it's fascinating to watch it because you can expand it in and out, and you can see the fractal nature of the scaling of all of these items working in perfect harmony. Here's an example of, this is a model that George put together showing these blue conical figures. That is the geometry of the Russian pyramid. It's the geometry of fractal scaling. It's the geometry of platonic solid scaling. And so it clearly indicates that all creation starts from a point of creation, but that expansion is occurring precisely within this geometry, and that this seems to be the preferred pathway and the pathway that nature would naturally use in the absence of outside forces to create our physical reality. And again, we've seen that with respect to light and sound and wind and so forth in nature already. So this is just a geometric proof that this seems to be nature's preferred pathway for scaling. And finally, here's just an integrating overlay showing how the two horns of the torus can be represented by the geometry of Goldden ratio scaling, and serve as a model, a theoretical model for how all of this is coming together. For more information on this model, we're not going to spend any more time on this. I put together last year a long documentary that goes into this in more detail, and you can see that at our YouTube or Rumble channel for the Pyramid Science Foundation, and look for the Goldden ratio and the organizing principles of the universe. This ends section 5, and from this point forward, we're going to be talking about Goldden ratio scaling and fluid dynamics. Part 6, Goldden ratio scaling and fluid dynamics. Well, we're finally at the good stuff, so I hope I haven't lost too many of you so far, but from here on out, we're going to be talking about Goldden ratio scaling in fluid dynamics. You see in this cover collage a few of the many examples that we're going to be talking about. We're going to see GRS in fish, the fastest fish in the ocean. We're going to see it in hypersonic weapons. We're going to see it in bullets and artillery. We're going to see it in flying birds. We're going to see it in ancient aeronautics. We're going to see it in contemporary jet aircraft, both commercial and military. We're going to see it in the nozzles of jet engines and rockets and hypersonic vehicles. And we're going to see it in land vehicles as well. So we've got a lot of different places that we're going to see this angle. It's so universal. It's amazing that this hasn't, been discussed prior to now. But before we get started with all of these various specific examples, I do want to introduce fluid dynamics and the basic ideas to those who are not mechanical engineers, and that's probably a good number of the people in the audience. So for those of you in the world of engineering, some of this may be repetitious, but I think it's important that we go over it for the rest of the audience. So by way of introduction, fluid dynamics is a subdiscipline of the field of fluid mechanics that describes the flow of objects through gases and liquids. It has several subdisciplines, including aerodynamics, the study of air and other gases in motion, and hydrodynamics, the study of liquids in motion. Fluid dynamics has a wide variety of applications, a lot of which we're not going to get into today, but the most important thing that we're going to want to see is that from my research, based on observations of literally thousands of examples, Goldden ratio scaling is the geometric angle found in the geometry of all of the fastest birds, the fastest fish, airplanes, missiles, rockets, and even hypersonic vehicles. GRS is also the angle, interestingly enough, found in rocket, jet, and hypersonic engine nozzles that maximizes thrust. So if you remember back to our discussions of implosion and explosion, it's the same geometry that we're using here, except in one case, we're using it to provide thrust, and in the other situation, we're using it to minimize resistance. So it's important both in terms of reducing that drag force that we're going to be talking about, but also propelling the vehicle as quickly as possible through its medium. Now, despite the vast number of examples that you're going to see here, linking GRS with the minimization of drag and the maximization of thrust, there are no underlying theories in fluid dynamics that I have been able to find to explain this phenomenon. And that's because the equations and the kind of the worldview of mechanical engineering doesn't include any theories of the ether or sacred geometry. So included, just to finish up this little introduction, I've included in the appendix. We're not going to do all of these because it would be boring, but I have over 500 additional examples to complement the ones we're going to be going through in the main part of this presentation, which will provide, additional documentation. I've got every commercial airplane that's ever, a jet airplane that's ever been built, every rocket, every missile, every military aircraft, and so forth that isn't covered in the main body of the presentation. Now, I want to discuss just basically some concepts that are important in fluid dynamics for those not familiar with it. And one of the key concepts is a laminar versus turbulent flow. When an object is flowing through a liquid or a gas, either two types of flow occur. And that depends on a number of factors, but primarily the velocity and the viscosity of the fluid. And I say mainly because geometry is very, very important. And those two types of flow are laminar flow and turbulent flow. Now, laminar flow, lamina, that's like a sheet, is the property of fluid particles to follow smooth paths in layers, with each layer moving smoothly past the adjacent layers with very little or no mixing. At low velocities, the fluid tends to flow without this lateral mixing or turbulent flow, and adjacent layers slide past each other fairly smoothly. In laminar flow, the motion of the particles of the fluid is very orderly, with particles close to a solid surface moving in straight lines parallel to that surface. Turbulent flow, on the other hand, is fluid motion characterized by chaotic changes in pressure and flow velocity. It is in contrast to laminar flow, which occurs when a fluid flows in parallel layers with no disruption. So just to give you some, a visual of what we just learned here, here's laminar flow, and this is assumed to be in a pipe. So this is a liquid medium that we're looking at to make this simple. But you can see on the edges of the pipe, the flow of, although it's all in straight lines, the flow nearest to the edges of the pipe is slower than it is in the middle, and that's because of friction or drag that occurs between the inside of the pipe and the first layer. Let's assume this is water that's flowing through the pipe. As each of these layers gets further and further away, their speed increases, and so by the time you get to the middle, that's where you see the fastest speed with which the water is flowing. Turbulent flow, on the other hand, as you can see, is characterized by eddies and disruptions, and this results in a much slower flow of, in this case, water flowing through this pipe. And it was really in that context, we're going to be talking about Victor Schauberger later, but that was one of the key ways in which he used Goldden ratio scaling to eliminate, or to minimize, I should say, the turbulent flow in pipes so that the water would flow through them more quickly. Now we're going to discuss briefly drag itself. And what is drag? In fluid dynamics, drag is the force acting opposite to the motion of an object. So if you're thinking, if you ever put your hand outside the car window when you were a kid, that you could feel that pressure, that resistance, that's drag. And so drag can exist between two fluid layers, two solid surfaces, or between a fluid and a solid. Drag forces tend to decrease fluid velocity relative to the solid object in the fluid's path, as well as decrease the velocity of the solid object. So that kind of makes sense. My arm, when I'd put it out, I'd have to press hard to keep it in the position that it was normally, would be without any wind. And similarly, the wind that was in front of my hand when I held it out the window was being slowed down relative to the speed of the car that I was in as well, so that there was a backup and essentially an additional higher pressure in that area as it hit my hand. Well, unlike other resistive forces, drag force depends on velocity and specifically varies with the square of the velocity. And why this is important is it means that precision in minimizing drag is most critical at very high speeds. As a result, the faster an object flies or swims, the more pronounced the presence of Goldden ratio scaling is going to be in the anatomy or the design of that object. So what that means, we're going to be seeing things like helicopters. Well, helicopters don't fly all that fast, and it's not all that important that they, have minimize drag for purposes of increased velocity. But if we're talking about a hypersonic vehicle that's going at Mach 27, rather than 100 miles an hour, 150 miles an hour that a helicopter might fly, well, then that's going to make a tremendous difference. And you're going to be able to see that geometry, that GRS geometry, much more clearly in these faster vehicles. So now let's go over the basic drag force equation. The key thing here, we'll go through the terms. Drag force is equal to 1/2 of the drag coefficient. Now we'll talk about that in a minute. Times rho, or the density of the fluid, whether that's a gas or a liquid that we're flowing through, the velocity squared of the object passing through the object, or the fluid, and the area of the object passing through the fluid. Now, what drag coefficient itself is not something that can be computed mathematically. Mechanical engineering, at least right now, mechanical engineering is not able to make precise calculations of drag coefficient, but rather rely on water and wind tunnel testing, the rapidly growing field of computational fluid dynamics, and historical observations, all a costly and time-consuming process, which, at least with respect to this a question of drag minimization, can be found by using Goldden ratio scaling. And once again, velocity is very important because the drag force is a function of the square of the velocity. Now, this is the similar information that's coming from the Glenn Research Lab Center at NASA. They're using, it's the same equation that we saw before, but the important thing here in the second paragraph down here, the coefficient CD contains all the complex dependencies of drag and is usually determined experimentally. And the choice of reference area affects the value as well. But the key thing here is that this is confirming that there's no mathematical computation that will show you how to minimize drag in all situations. However, we're going to see that Goldden ratio scaling is the optimal solution for all of this. Now, here's a table of drag coefficients that you can find on the internet, and it shows you how the structure of different objects will affect the drag coefficient. If you have air flowing, in all cases here from the left to the right, if you encounter a circle, for example, you see that there's a drag coefficient of 0.47. Whereas if you have a half circle, that drag force is reduced, just as it is if you have a more conical structure at the front. So conical and kind of semicircle seem to, at least at first glance, to be roughly similar. But when you interject things such as squares or cubes, or even diamond-shaped objects, you see that the drag coefficient goes up quite a bit more. If we go down to the bottom, the last two examples are quite aerodynamic, far less drag force than we find in these other examples. So it shows how the design of the object is critically important, but it also shows the tremendous differential and the need to design the bodies of aerodynamic vehicles as closely as possible to minimize drag. Now, this is perhaps one of the most important slides we're gonna talk about today because this is the Mauser bullet. This is a German bullet that was used in both World War I and World War II. And it was adopted by the German Empire in the early 1900s and was the cartridge that was used by the German military in both World War I and World War II, and was adopted by many arms manufacturers because it was so aerodynamically sound, and it would maintain its motion, and it was very, very stable. So this became kind of the model of all of the other bullets, and many of the even the Axis, excuse me, the Allied powers, as well as the Axis powers, adopted this during World War II. Most importantly, however, this bullet served as the model for the V-2 rocket used by the Nazis scientists during World War II, developed by them, and the V-2 rocket ended up being essentially the model for modern aerodynamics and aeronautics into the latter half of the 20th century and on through to today. So this is an extremely important uh, uh, thing to keep in mind. Why? Because we see that this bullet has this very precise geometry that, in its nose cone. And we're going to see this geometry showing up all Goldden ratio scaling throughout all of these other documents that we're going to be looking at. Now, this is what's called the Sears hack body. This was actually this was done theoretically. The bullet, as you know, was the result of actual experimentation and use in the real world. So what's interesting is that in the early German scientist Wolfgang Hack did this in 1941, this model, and what it's supposed to demonstrate is a theoretical shape with the lowest theoretical drag in supersonic flow. And this body, again, has served in theoretical, this is used in theoretical computations and so forth, in modeling drag. But what's interesting is that when you look at the angle that shows up at the edge of this, it's exactly equal to the angle of Goldden ratio scaling. So the mathematics that seem to have been behind the theory that of the Sears-Hawk body, as well as the practical application of this in bullets, demonstrates that this geometry is the geometry that will minimize drag. Now, before we get started, this is the last slide before we begin looking at actual examples, but I just want to go over again something I stressed a minute ago. The precision with which we find Goldden ratio scaling is influenced by the density of the fluid, whether that's air or water, the speed of the object, design constraints such as cockpits or where you're going to put an engine on an airplane, those sorts of things, and the design objective. Sometimes speed is not the only thing that we're out to do. Stability is important. Lift in aerodynamics is highly important. So you're going to have all of these other kinds of competing, demands on the aerodynamic structure of a body or a vehicle. So just keep that in mind. But to the extent that speed is the primary concern, GRS is most readily apparent, whereas in lower speed objects, as we said, design constraints can mask it to some degree. Now, in the appendix at the end, I put in over 500 examples that you can look at over and above the ones that we're going to be discussing in the main body of the presentation. So for those of you interested in looking for specific models of commercial airplanes or rockets or sports cars or whatever it may be, look in the back and you'll very, very likely find what you're looking for. At long last, we're ready to start looking at examples of golden ratio scaling. And we're going to start in the animal kingdom, and we're going to divide that into two parts, waterborne and airborne. And so first, we're going to look at waterborne animals. Now, researcher Victor Schauberger developed his ideas for free energy and anti-gravity technology from studying nature, particularly the trout. And Schauberger found, as we're going to see, that golden ratio scaling shows up in many, many aspects of the anatomy of the trout. And he actually knew about golden ratio scaling. We're going to see that diagram later, but it's unclear whether he learned this from another source or, like me, I reverse engineered this in the Russian pyramids, whether he reverse engineered it from the geometry of the trout. But no matter, the examples here demonstrate that GRS is found in every one of the fastest swimming, waterborne creatures, and it plays a significant role also apparently in the strength of animals such as the dolphin and others, where when they use this geometry, they're able to propel themselves like the trout and actually the whale as well into the, high into the air. So but you see this in so many different places. So let's get started. Here's the inspiration that of Victor Schauberger. This is the diagram of the trout. And we're going to find that 27309 geometry all over this fish, and you're going to see it elsewhere very soon. So if you look at the back half of the fish's anatomy, you can see that it's scaled just like all of our other objects with the 27309 geometry. And if you look up here at the fin, it's got the 27309 geometry in it as well. And if we look down here at the bottom, we're going to see in that other photo that the GRS geometry shows up in the front as well. Now you're going to say, and I agree, this is my point, that we have to take consideration the fact that there's a mouth and eyes and so forth that have to fit into this fish anatomy, so it's not as easy to see in the front. But once again, we see the same geometry in the tail fin as well. So it's literally cooked into the geometry of the trout. Now on the right-hand side, we've got a straight-on view of the trout, and you see that its anatomy goes up with this same geometric angle. And above that, I've got a perfect example, which we'll see later in submarines, of a German submarine blueprint that demonstrates that geometry shows up in the submarine as well. So literally, golden ratio scaling is everywhere inside the trout, which was the inspiration, as I say, for Victor Schauberger. Now, this is a whale, an orca whale. And you see it particularly well in the back of the orca whale. A little harder to see it up front, so I didn't include that in my analysis, but it's certainly in the back. The next example, another whale, humpback whale. You see it both in the snout. This particular whale, as you can see, has lots of barnacles growing on it. But anyway, and it's another one of these animals that can jump high into the air. One of the ways that it's able to do that, and we should make this distinction, the whale, and we'll see other animals that are mammals, such as, we'll move forward here, the dolphin. The back fin is actually in the horizontal plane. And these are both mammals, the whale and the dolphin. And so they use, in that context, they're using their back fin to help propel them up to the top and I guess to be able to breathe. But that's in distinction to the shark, which is actually a fish, not a mammal, and we see that it's in the vertical plane. But no matter whether it's a mammal or a fish, we see these sea creatures both in the front anatomy and in the rear. We're seeing that. Here's on the right, we see a picture from below of the great white shark, and we see the geometry in that plane as well. Here's one of the Greenland shark showing this geometry in the tail. And here's a dolphin that we mentioned a minute ago. We see it in the rear as well as in the front. And the dolphin, here's another Atlantic humpback dolphin that has this in the rear. And here's an example of a flying dolphin. So you can see that fin is in the horizontal plane, but they're able to use this geometry to help propel them, high into the air. It's pretty fascinating. Now, here are crocodiles, and again, you've got to have a mouth and a snout, but you can see that this geometry is showing up both on the side view, the top view, and the bottom view of the mouth of the crocodile. And similarly, here's an alligator with the same types of views, the side and the bottom, with the very same geometry as well. This is one of the fastest fish, the bonita. You see it, again, as they get faster, you start to see this more pronounced, but in the front, you can see this geometry more pronounced than you could in some of the other fish, and it's obviously there in the rear as well. The tuna, the same thing in the back. You see this geometric angle. The mackerel, you see it in the front and the rear. Swordfish, this is a great example. It's very, very easy to see the Goldden ratio scaling geometry in the front end of the swordfish. And the same thing with the marlin, and you can see it in the rear of the marlin here. And here we have sailfish, and finally, here we have an example of the barracuda. Now, next, we want to move on to looking at it in airborne creatures and birds. So similar to waterborne animals, birds also demonstrate Goldden ratio scaling in their body design. And these examples include the 10 fastest flying birds on Earth. So we're going to start with the world's fastest flying bird. That's the peregrine. It's been tracked as fast as 242 miles an hour in its dive. And we're going to see this geometry shows up not only in the front and the rear of the anatomy of the peregrine falcon, but it also appears in the angle of offset of the wings to the angle or the direction of motion. And we also see it in the rear of the bird as well. So here's some more pictures. We see this 76-345 in the angle of the wings, and we see it in the front of the bird. This is called the Saker falcon. It's the second fastest bird on the planet. You see again the Goldden ratio scaling in the back end of the bird, as well as when the wings are flared out, we see the same geometry as well. And we see the same 27-309 angle. I'll call it offset in the wings. That number of 207, I had to measure it this way, so you just subtract 180 to come up with 27-309. And here are three examples, which I think are going to be interesting to consider as we get into fluid dynamics in vehicles. This is the Osprey, and when it dives, I saw this and I couldn't believe that it was anything more than a fluke initially, but I found three different examples of this where this 76-345 degree angle shows up again. And I've got implosion here because what I believe is happening, this angle, there's a high pressure area that's going to be built up in front of the wings as the Osprey is diving, but there's a low pressure area in the back where the wings are folded inwards. And this is an example showing that implosion occurs within this geometric angle as well, and that by using this geometry, they create the least amount of flutter, least amount of turbulence, and improve laminar flow. So another example. Now here's a pelican, similar. It's nowhere near as fast as these other birds, but we see when it dives as well, we see this 76-345 angle showing up in the wings as it's diving as well. And then here's the white-throated needletail. As you can see, the geometry shows up much more distinctly in the back than in the front. But I wanted to show you, because this is so important to see, that the back end of the needletail looks exactly like that of a commercial airliner and has the very same geometric angle. So it's obvious that this aerodynamic function is important not only for birds but for airplanes as well. And then this is a Eurasian hobby, same thing. The back of the bird has this geometric angle. This is the spur-wing goose. You see it in the back of the goose as well. And then we have the red-breasted merganser with this geometry in the back of its anatomy as well. Here's the gray-headed albatross, which has this geometry as well. So, and then we're going to end up here with the canvas back. And here in this example, we can see the geometry in the front a lot more easily than we can in some of the other birds. And it's there in the back as well. So just remember when we saw that Sears Hawk model, that we saw that we needed this aerodynamic geometry in both the front and the rear for it to be as aerodynamically sound as possible. Golden ratio scaling and ancient aeronautics. In this section, we're going to be exploring the history of aeronautics, despite what many of us may have been taught in school. We've known how to fly for thousands of years at least. We can see this in the ancient hieroglyphs and drawings, artifacts that we can find around the world. And the interesting thing is that the angles of aeronautics have not changed over time. That shouldn't be a surprise. So we're going to see the very same angles of 27.309, 76.345, and 13.654 that we've seen in or will be seeing in contemporary aeronautics as well. So let's get started. We're going to start with perhaps the oldest aeronautic device that I was able to find that has been kind of in continuous usage since its origins and continues into the present day, and that's the boomerang. The boomerang is at least 20,000 years old and is used currently by Australian Aboriginal tribes, Native Americans, and residents of southern India. Now, what's important, this is on the left is a classic boomerang. This is a boomerang that will travel in a circle and come back to you with some practice. There are others that are not symmetrical like this and have a longer arm on one end, and they are more hunting boomerangs, and you can throw those and they'll go in a straight line to attack, prey that you might be interested in trying to eat. So anyway, what's important here, we're going to be talking about airfoils a little bit later, but this will give you a bit of a preview as to how an airfoil works. If you look in the middle of the right diagram where my cursor is located, you're going to see what's called an airfoil. Airfoils are the objects, they're essentially wings, but in this case, An airfoil is perhaps a more appropriate term because this isn't really a wing per se. But anyway, they have this 13.654 degree geometry as well. So, this shows you we've known about this for 20,000 years at least, that we've known the basic principles of aerodynamics. Now, what's important, this is I don't know if they make left-handed versions, but this is assumed that you're going to be flying this with your right hand. You take your right hand, and put it where my cursor is right now, and fling it out to the side, like in front of you with your right hand. And so you can see that the upward edge, this is called the leading edge, is in the back on that side, but it's in the front on the other side, because in each case, those are the edges that are going to be leading into the wind, depending upon the part of the cycle that you're in, throwing the boomerang. But anyway, oldest example that I could find, and definitely shows that we've known about this for a long time. Now, these are some hieroglyphs from the New Kingdom Temple. This shows some flying craft, and this temple is in Egypt. Now, this is a famous hieroglyph, and you can see that there's a picture of what looks like a current-day helicopter. This picture could be a spaceship. This could be a boat, but I'm going to focus on these two because they have the angle most obviously of golden ratio scaling. So you can see it there in the front of that craft. The helicopter, it's particularly easy to see the 13.654 degree angle. Now here is a Japanese rocket ship cave drawing. This is in a cave in Japan, and is estimated to have been drawn about 5,000 BCE. You can see the GRS geometry both in the front and in the rear of the craft. And as we were showing on the first page here, it's except for the width of the body at its maximum, the angles that are found here are very, very similar to those found in the Sears hack body. And in fact, the angle at the front and the rear of the craft is identical. This is an Egyptian artifact called the Saqqara bird. This bird was actually found in the collection of a museum, and the individual who did the research on this found it and decided to write papers on it. And he drew the mathematics and drew blueprints of the bird and so forth. We're seeing that 27,309 angle on the side of the wing, just as we've seen it in birds that were in our survey here. For example, the Saker falcon. And then we see the GRS geometry in both the front and the rear of the main part of the body of the bird. And these are some artifacts from Colombia. They're called the Quimbaya artifacts. We can see here in this particular one that the golden ratio scaling geometry is in both the front and the rear of the craft. Here's another one where we can see it in the rear. Two more, actually, where we see it in the rear. And we see it in the angle of offset of the wings in this other example. So they clearly knew about these geometric angles and used them in making these objects. Here's another one. This is an Incan artifact of a flying machine, and we see this geometry there as well. Here's a Mayan alien artifact with the golden ratio scaling geometry. And here is a carving, Toprakale, which was an ancient kingdom of Ararat, which is in contemporary Turkey. So this was a carving of what was a craft of some sort depicting a human being flying. You can see the rocket engine motors in the back. I mean, it certainly looks like technology that could have come right out of the 20th century. So uh, what's interesting is that um, these objects are not talked about in our history books, and so we don't have this impression that we had all of these technologies in prior lifetimes. And then finally, to finish up this segment, we're going to end up with some 11th century Chinese rocketry. This was the oldest example of what I would call the current era, where we can find this geometry. But this is going to end our discussion of ancient um, uh, aeronautics. We're going to pick up in the 16th century in the next section. Golden ratio scaling and contemporary aerodynamics. In this section, we're going to look at the history of aerodynamics starting in the 16th century. And we're going to take this section, will take us all the way up through the time of Wernher von Braun and the beginning of late 20th century aerodynamics. But we're going to start in the 16th century with a segment on Conrad Haas and the Sibiu manuscript. And in 1963, a Romanian engineer named Doru Todoriciu investigated a manuscript of about 450 pages in the National Archive in Sibiu, Romania. The manuscript had been known as a work on different problems of artillery and ballistics, but Todoriciu analyzed it with regard to its scientific and technological content. And what he found was that the author of the third part of this manuscript, named Conrad Haas, described remarkable ideas about rocketry. Between 1529 and 1569, Haas wrote the manuscript, which seems to be the very first description of the principle of a multi-stage rocket. He describes and depicts rockets with 2 and 3 stages, talks about the bundling of rockets, stabilizing fins, and liquid fuel. Haas's multi-stage rocket design was used for a number of space programs, including NASA's Mercury, Gemini, and Apollo projects. So we can see here, we've known about these concepts have been around for quite some time, and were not just invented by Nazi scientists during World War II. Now, here's another example of golden ratio scaling, and we're finding this one in the 17th century rocketry designs of Kazimierz Siemienowicz, who was a Lithuanian rocketry pioneer. And as you can see, it certainly looks like there's nothing new under the sun here. The design of this rocket is strikingly similar to that of the Avangard hypersonic glide vehicle from Russia. And they both have the very same geometry. Here is a rocket, excuse me, from 1812 that was invented by the British rocketry expert Congreve. This particular rocket was used in the War of 1812 against the United States during the War of 1812. So we can see how it continues. Now, this is not rocketry per se, but what this demonstrates, again, if you look at the Native American arrowheads and fletching that they used, you'll see that these arrowheads and fletching all have this geometry. So this was literally seemed to be common knowledge, this knowledge of aerodynamics across all cultures. And You can see here more examples of the fletching and arrowheads uh, depicting the Goldden ratio scaling geometry. Here's another example. These are iron furnaces. Before we began the steel age in the late 1800s, the iron furnaces that populated the Northeast all had this geometry, and that geometry carried through into the ovens and the chimneys themselves. And we'll see this in a contemporary context here in a few minutes, but essentially this geometry is the one that seems to optimize, and again, because of laminar flow, optimizes the flow of air through the system and thereby maximizes heat. Interestingly enough, when you look at swords, swords generally have this Goldden ratio geometry as well in their tips. I can't explain that exactly, but I would imagine that as when you see this upcoming slide, you'll get an idea as to why that may be the case. This is a contemporary wood splitter attachment that you can put onto your drill to help you, split a piece of wood rather than having to do it with an axe. And what here's the 27309 geometry showing up in this contemporary wood splitter. So my guess is that the sword acts in much the same way. That geometry, just as it cuts through air and cuts through water most effectively, it cuts through solid materials as well. Here's another example of this geometry in a fluid dynamics context in the 19th century. This is the Sibley tent stove. Again, very same geometry as the iron furnace that we just saw. And this particular stove was used during the Civil War you could put it inside your tent, as you can see here, and it used minimal amount of fuel because it was highly efficient, but it was great for warming up the tent in the wintertime and with the minimum amount of fuel required. Taking that example into contemporary times, we see this geometry as well in power plant cooling towers. These natural draft cooling towers have no engines or fans to pull the air out from the tower itself. And in fact, it relies on, the natural mechanics of airflow. And what they find, the basic process, you take hot water from either a nuclear or a coal-fired plant, and it is piped into these cooling towers. And about a third of the way up, there's a system of sprayers that turn it into a mist. And that's why you see the steam coming off, because it evaporates. And the evaporative action creates a suction. If you can look down at the bottom of the cooling tower, that's an area where air can be brought into the system, and the geometry of Goldden ratio scaling turns out to be the optimal angle. Once again, minimizing turbulence, maximizing laminar flow, helps to maximize the flow and the efficiency of the cooling tower. We're now going to talk about a 19th century inventor named John Keely. John Keely was an American inventor from Philadelphia who discovered a new motive power, which he described as sympathetic vibratory physics. He invented a water-based free energy machine, which was poised to be brought into commercial production, but never hit the market for a variety of reasons. Keely was a member of the Theosophical Society, and this is a society that Rudolf Steiner and Victor Schauberger also belonged to. And I believe that this society acted to protect some of this ancient knowledge. That may have been, as we'll see, where Victor Schauberger learned about Goldden ratio scaling. We're not sure, but upon Keely's death, his papers and research were sent to the Theosophical Society for safekeeping because he was vilified after his death, even though many people claim to have seen the experiments that he did with water and free energy. We're going to see some of that here in just a second, how it may have worked, and knew that it worked. But this is one of the first of several examples we're going to see where this information was either vilified or suppressed, apparently to keep it out of public view. So what I'm going to show you here, this is he had a free energy water machine, and what I'm showing you is one of the vials that's attached to it. It had this 76-345 Goldden ratio scaling geometry in it. That wouldn't have been significant in and of itself, or as significant, had it not been for this diagram that I found in his works, which describes a vortex and essentially the horns of the torus that we discussed earlier with exactly the same geometry. So there's nothing absolutely certain here, but it looks as though he knew about this geometry and used it in his water devices. Here's another example of 19th century free energy technology. This is the Royal Palace in Phnom Penh, Cambodia. It was built in the 1860s. And if you'll see on the right-hand side, once again, just as we saw in the ancient Hindu temples, we find this Goldden ratio scaling coil at the top. But most importantly, this palace is still producing free energy today. And this comes from a YouTube video that you can go out and see. All you have to do is search for the Royal Palace, Phnom Penh, Cambodia, free energy, and you'll find this video. But you can see that it is acting, on the atmosphere, and this may be a situation where we're essentially collecting or using the ionization available in the atmosphere, and also from the geometry of this pyramid. We're going to be talking a lot more about that in a few minutes. Now I want to kind of start to get into 20th century work on aerodynamics. Konstantin Tsiolkovsky was a Russian and Soviet rocket scientist who pioneered astronautics, along with Hermann Oberth and Robert Goddard, Oberth from Germany and Goddard from the United States. He's one of the pioneers of spaceflight and the founding father of modern rocketry and astronautics. His work later inspired Wernher von Braun and leading Soviet rocket engineers Sergei Korolev and Valentin Glushko, who contributed to the success of the Soviet space program. Now, there's not a lot of information about his designs, but here are three. This is on the left, a design for a vehicle, a rocket that he designed with the Goldden ratio scaling. We see this rocket design here as well with Goldden ratio scaling, and we see a design here that looks strikingly similar to the Sears-Hawk body that we have seen and talked about previously. So he was certainly knew about Goldden ratio scaling and incorporated all of this into his rocketry designs. Robert Goddard, that's the Goddard Space Center for those in the United States, was an American engineer, professor, physicist, and inventor who's credited with creating and building the first liquid-fueled rocket. Now remember, we saw that from Conrad Haas in the 16th century, but it was successfully launched on March 16th, 1926. By 1915, his pioneering work had dramatically improved the efficiency of solid-fueled rockets, signaling the era of a modern rocket and innovation. He and his team launched 34 rockets between 1926 and 41, achieving altitudes as high as 1.6 miles and speeds as fast as 550 miles. Here's a picture of Goddard with a couple of his team, and we can see it's tough to check out the fin geometry, but we're going to be doing that on some other craft here in a minute. But you see that the nose cone has the Goldden ratio scaling geometry. A Russian who was important as a engineer, rocket engineer, and spacecraft designer during the space race was Sergei Korolev. We mentioned him a moment ago. On September 8th, 1945, less than 1 week after the end of World War II, Korolev was brought to Germany along with many other experts to recover the technology of V-2 rockets from Germany. The Soviets worked with German specialists to understand and replicate the rocket technology, placing a priority on recreating the entire German V-2 rocket. He invented the R-7 rocket, Sputnik 1, and was involved in the launching of Sputnik 3 and Vashgod 1, the first manned spacecraft. So now we're going to talk about Victor Schauberger. We've talked about him before. I want to spend a little time on Victor. Even though Victor was not directly involved in aeronautics, he's using the same Goldden ratio scaling techniques that we're angles that we're seeing in all of this aeronautics. So it's important to bring him in at this point. He was an Austrian forester, naturalist, and free energy inventor. He studied nature as his primary source of inspiration. We talked about that earlier. Many of his theories evolved from observing trout swimming upstream. Using the GRS geometry he found in trout, he proceeded to make a number of successful water implosion devices based on the flow of water in spirals. Schauberger was forced to work for the Nazis on free energy and anti-gravity technology during World War II. After World War II, he was coerced into signing over all of his technology to American business interests in order to have his confiscated passport returned to him so that he could go home back to Austria. And when he came over here, he is alleged to have been in ill health, but within 5 days after returning to Austria, he died. So his drawings, his technologies went into the hands of American business interests. However, this was done under highly dubious circumstances. The fact that his passport was taken from him upon his arrival makes it sound as though there was more to this than meets the eye. And none of his technology has really seen the light of day. We have one drawing which we're going to show here in a minute, which seems to indicate, well, does prove that he knew about Goldden ratio scaling, however, and that seems to have escaped the censors. Victor Schauberger realized that there were two forms of motion in nature. We've talked about this, outward and an inward explosion and implosion, and that the outward masculine explosive motion is expansive and destructive and creates heat, pressure, and even death, and that the inward feminine implosive motion produces coolness, suction, powerful vortices, and health benefits, and is used to build up and energize, and is therefore life-enhancing and life-promoting. This is a picture of his Vortex water generator that he had developed for home use. Sources indicate that this device produced 10 times over unity for energy. And for those unfamiliar with that term, it oftentimes requires a certain amount of energy to be put into a machine or a system in order for the resulting output of energy to occur. And to the extent that the energy that comes out of the system is greater than the amount of energy that's put in, it's called over unity. And so this was apparently a very powerful over unity device. And we can see here these copper tubes would be filled with water and they would spiral down using Goldden ratio scaling. Now we're going to look at a few of his drawings. We'll start on the right. We've seen these trout depictions before, but these are the very same these are the drawings that Schauberger put together about the trout. And you can see the same Goldden ratio scaling angles that we saw on the live trout showing up here. Now, in the bottom right-hand corner, this is an example of some spirals that Schauberger put together. And the purpose of these was to have water flowing through a pipe spiraling towards the center of the pipe with the intention of reducing drag, and it actually did speed up the flow of water through pipes in those systems that he installed this. Moving on to the center, we have what's called the repulsine. This was a water-based device. It looks a lot like a fish, but you can see that the structure itself has this same 76-345 Goldden ratio scaling geometry in it as well. Moving over to the left, it's said that the Heinkel, which we're going to talk about in a few minutes, which is the very first jet airplane to be designed and successfully flown, that the inventor stole a lot of the technology from Schauberger. Now, whether that's true or not, I'm not sure, but sure enough, the Heinkel has the Goldden ratio scaling in it, so it looks as though if it was stolen from him, they did a good job of copying it. Now, this is an important page because you've seen how I came up with Goldden ratio scaling before, and this depiction, it's in German, but it essentially depicts that seashell that I showed you early on in this documentary, and it's using that geometry and showing how the Goldden ratio is scaled through the seashell. So he knew about this and used Goldden ratio scaling in designing a lot of his devices. We're going to move on now to the early 20th century. We're going to talk briefly about the Vimanika Shastra. And the Vimanika Shastra, or in English, the Science of Aeronautics, was a 20th century text in Sanskrit. It makes the claim that the Vimanas mentioned in ancient Sanskrit epics were advanced aerodynamic flying vehicles. And the existence of the text was revealed in the early 1950s by G.R. Joshua, who asserted that it was written by Pandit Subbaraya Shastri, who dictated it during 1918 to 1923. A Hindi translation was published in 1959, and the Sanskrit text with an English translation was published in 1973. It has a number of chapters about a number of different kinds of vehicles, and it is important to see that one of those, the Shakuna Vimana, is actually a vehicle that contains Goldden ratio scaling. So we see it here as well. And here's a picture, a depiction of that ancient flying machine from the Vimanika Shastra. Now we're moving on into more contemporary mid-20th century. Wanted to talk to you about Albert Pelterie, who's a French aircraft designer and spaceflight theorist. He's referred to as being one of the founders of modern rocketry and astronautics. One of his important things was in rocketry was to develop the rocket nozzle. Now we're going to be talking about these more in another chapter, but I wanted to show you that these rocket nozzles are all demonstrating the Goldden ratio scaling geometry. Again, the explosion that we talked about at the beginning of the series is the thrust is optimized apparently by the use of this geometry. Now we're going to just briefly talk about Nikola Tesla's Wardenclyffe Tower. Sure enough, Wardenclyffe Tower has this geometric angle as well. Not sure if that had anything to do with the free energy that was generated, but when I show you this overlay, you might begin to think that it just might. We saw Solomon's Key earlier, and we saw George Leoniak's overlay of sacred geometric and Goldden ratio circles and the like inside that. But when you overlay Solomon's Key onto Wardenclyffe Tower, it looks as though it's a perfect match. So I don't know if this was an inspiration for him, but once again, we're seeing Goldden ratio scaling involved in free energy production. Hermann Oberth was an Austro-Hungarian-born German physicist and rocket pioneer of Transylvanian Saxon descent. Now, if you remember, we saw that Konrad Haas came from this very region in Romania and the like, so there seems to have been a lot of knowledge in that part of Eastern Europe during the 15th, 16th century. He's considered one of the founding fathers of rocketry and astronomics, worked for the Nazi Party and received the War Merit Cross in 1943. Now, his big claim to fame is rocket nozzles. And sure enough, he was in charge of the rocket nozzle for the V2. And guess what? Lo and behold, Goldden ratio scaling is showing up once again. Going to look now at the very first jet airplane. We talked about this a minute ago, the Heinkel 178, the aerodynamics of which were allegedly stolen from Victor Schauberger, but we can see Goldden ratio scaling in the front of the plane. In these blueprints, we can see it from the top view in the front and also in the rear of the aircraft. Here's a side view again, and we see it in the front of the aircraft. So clearly they knew about this. They knew about the aerodynamics. And as we talked about earlier, of course, they were using, at least the developers of the V2 rocket knew, were using the bullet of the Mauser, which had this geometry as their guide. But we'll get to that in a moment. Now, here's another airplane called the Heinkel HE-176. This was a rocket-powered manned airplane, and you can see the geometry in the rear of that plane. Here's the V1 rocket. This is, again, another product of Nazi Germany. The V1 rocket demonstrated the GRS geometry up front, as well as in the rear. And here's the world's first hypersonic aircraft, built by Nazi Germany in the 1930s, called the Silbervogel. And we'll see here, it's got the Goldden ratio scaling in the front of the nose cone of the aircraft. Here's a blueprint of it. We can see the 13654 geometry in the front because this design had a very flat bottom to it. They didn't want to have that geometry floating down to the bottom of the aircraft. When we look from the top view, however, we see the 27309 GRS geometry. And here is the Messerschmitt 262 in Nazi Germany, the first jet fighter. Again, GRS in the front, and then the 13654 angle in the rear. Probably that was due to the fact that these jet engines were blasting through the, on the bottom of the airplane, and they didn't want to, it was inappropriate to put that geometry in the back of the plane at the bottom. This is Secondo Campini. His major claim to fame was that he developed what turned out to be the second jet airplane. He began work with Italian manufacturer Caproni to develop the jet aircraft, the Caproni Campini CC-2, which first flew in 1940. What's different is that he used a conventional piston engine, but the aerodynamics of his plane still demonstrated, this geometry. So after World War II, we're going to see some of his work in the United States. He came to the U.S. To work at the request of Preston Tucker, who was owner of a brand of automobile called the Tucker automobile. And he wanted him to help him, design his cars. And so he came here. And after that, he found other employment working on a number of military projects for the United States government. And here's a picture again of the Campini plane that he developed, the second jet airplane to fly in the world. This is something called the Project 346 rocket. This is an unmanned rocket. It looks a lot like an airplane. It was jointly developed, interestingly enough, by Germany and the Soviet Union in 1948. They worked on this jointly, and you can see the Goldden ratio scaling in this craft as well. And here's another one from the Soviet Union called the Samolyot 5, which seems to be a plane that maybe was to land on ice, but it's a jet engine, and it has this geometry as well. Now we're getting to contemporary times. It's now time to talk about Wernher von Braun. He was a German-American aerospace engineer and space architect. He was a member of the Nazi Party, the leading figure in the development of rocket technology in Nazi Germany, and later a pioneer of rocket and space technology in the United States. He helped design and co-develop the V-2 rocket during World War II. In 1960, his group was assimilated into NASA, where he served as director of the newly formed Marshall Space Flight Center and the chief architect of the Saturn V super heavy lift launch vehicle to propel the Apollo spacecraft to the moon. So very impressive career for von Braun. We're going to look first at his V-2 rocket that he developed during Nazi Germany. We can see that the rocket had the GRS geometry in the nose cone. And we also see that it had this geometry in the stabilizing fins. A lot of the real effort that had to be put into the V-2 rocket had to do with stabilization. The aerodynamics that were used proved to be quite adequate, but stabilization and the fins became a very important part of that stabilization process, along with a variety of gyroscopic mechanisms that were built into the internal workings of the rocket to keep it flying, in the proper direction. So why is one thing that's really striking here, and we're going to talk about nozzles again in another section. Wernher von Braun knew that Goldden ratio scaling was the proper geometry for developing the geometry of the rocket nozzle for the V-2 rocket. And as you see here, this fits like a glove. I don't know if he knew this exactly, but my measurements are extremely accurate when I have a clear diagram like this of sufficient size that I can measure over a great distance. And this matches just spot on. So it looks to me like they knew they were using Goldden ratio scaling to do this. I can't prove it, but the measurements are just too precise to believe anything else. And then to finish up in this section, this was the Explorer 1 rocket that he developed once he came to the United States. You see that GRS in the nose cone. And then you see, however, they've changed the angle of the fin. And this, to me, is the more appropriate, from what I now understand, to the 13654, but it's all Goldden ratio scaling. And finally, we're going to talk about the United States Space Shuttle Challenger. This, again, was developed by von Braun, and it has this exact geometry as well. Before we finish this section, I want to talk about the Russian pyramid implosion free energy research as well. You're seeing this same geometry everywhere. You see it in aerodynamics, you see it in explosion, you see it now in implosion with the Russian pyramid research. And again, this is where I started and learned about this geometry to begin with. But what's important here is that there's a huge ionization field that's developed by this pyramid, which is, to me, proof of the implosion process in effect. And the research data from the Russian pyramid research indicates that if the ionization field from the pyramid were to be reproduced electromagnetically, it would require the combined energy generating capacity of all the power plants in Russia. Another example of this free energy capacity, they placed capacitors at the top of this pyramid spontaneously, and they spontaneously charged and blew upward into the sky. The energy field of the pyramid could be detected as far as 185 miles away. Now, amazing increases in immune function, life expectancy, and agricultural production are all part of the research associated with this pyramid. What's important here is that we mentioned earlier that the Great Zimbabwe Ruin has a huge ionization field associated with it. The Russian pyramids have the same huge ionization field associated with it. And the only thing that they have in common is their geometry, and that geometry is the geometry of Goldden ratio scaling. Now, amazing increases in immune function and life expectancy can be explained through research that was done in the University of London, where they found out that ions reduced viral load in humans by at least 90%. And that is one way of explaining the tremendous health benefits that occur. But we're going to be talking about ionization and free energy later in the segment. But as you can see, implosion, explosion, free energy, aerodynamics, and thrust are all associated with the very same geometry. And finally, I want to talk about a piece of research that was done in the 1980s or 90s, excuse me, again in Russia by another torsion physicist named Anatoly Akimov. And this is research on Goldden ratio-based free energy technology. And the article goes, in summary, says that the geometry of the ether is distorted by means of macro bodies, meaning objects, of a certain size and shape. And thus, torsion fields of considerable strength can be created. If the bodies have geometric dimensions with fulfillment of the Goldden section or Goldden ratio, then they can play the role of concentrators of the spinner or torsion field and act as free energy generators. So this is another, as we're going to see, piece of research that's hard to find in the United States. But I want to summarize what's happened to these free energy technologies because I think it starts to show a pattern. The Russian pyramid research that I was just referencing, that research was not allowed to be published in the West by any academic journals. So we don't have that data available to us in its entirety. We only have summaries of the results. Victor Schauberger's work, as I mentioned earlier, was forced under duress to license his technologies to a business to American business interests after World War II, and they've never surfaced again. Nikola Tesla's research, as we probably all know, was seized by the U.S. government upon his death. He used, looks like, Golden ratio scaling in Wardenclyffe Tower. John Keely's research back in the 19th century, we talked about, his research was discredited, and he sent it to the Theosophical Society for safekeeping. And finally, the Anatoly Akimov article, which talks about using the Golden ratio in free energy context, was censored. My access was censored to it by the U.S. Library of Congress, and I ultimately had to get a copy of it from London. They told me originally they had the article, and then I guess the censors found it, and they decided that they didn't want to let this out. So we've got 5 situations here where Golden ratio scaling were likely involved in free energy, and all of them are outside of the public domain. Golden ratio scaling in maritime vessels. In this section, we're going to be looking at all types of military vessels, whether they're submarines, boats, destroyers, you name it, as well as a number of boats that we see in everyday, use for personal use as well. So we're going to start with submarines. This is the Ohio-class ballistic missile submarine made by the United States. And what we're going to be seeing in all of these examples, it's very easy to see the GRS geometry in the rear of all of the submarines, and you can also see it in a good number of the front parts of the submarines as well. So in this page, we're going to see the front of the, we're going to be measuring the front of the submarine, both from a side view and a top view, so you can see that this is essentially conical in nature. So we see the geometry in the front of the submarine, and we see it as well in the rear. And here's a cruise missile submarine from China, and again we see it in the rear. In Russia, this is an attack submarine. It's called the Akula class, and we can see it in the rear of the submarines there as well. In the back to the United States, the LA class attack submarine has it both in the front. We can see it in the top and the side views of the submarine, as well as in the rear of the submarine as well. Now here's a submarine from Germany. It's called the Type 214 class, non-nuclear submarine. You see it in the rear of the submarine, as well as you can see the geometry in the vertical plane as well from the front. And if you remember, we saw this occur as well in the trout fish example that we demonstrated. And this is the example of submarine that we used in that example. And this is a cruiser, a Kirov class cruiser from Russia. We see this in the front of the ship. And this is a destroyer from Japan, the Asagiri class. We see it in the front as well. Here is an example of a racing sailboat. We'll see this geometry at the front of the sailboat. This is a kayak, and we see it in the front of the kayak as well. And here's a cigarette racing boat, and we see this geometry being used at the front of the racing boat as well. Now we're looking at torpedoes. All torpedoes have this geometry in the rear. Very few of them are going to have it in the front, but you do see it in every case in the rear of the torpedoes. And to finish up this section, I wanted to introduce those of you who are not aware of this to supercavitation torpedoes. Well, what are they? They're extremely fast moving torpedoes. You can see this diagram. Again, this is a Russian technology. Um, but the geometry shows up in the body of the supercavitation torpedo. What makes this unique is that there's what's called a cavitator at the front, which ejects gas through the nose of the torpedo, such that the torpedo itself is never bumping into water. It's always in a vacuous environment where water is not touching it. So fascinating technology. These torpedoes can go, I believe, in excess of 200 miles an hour. So an amazing technology for projecting things through water quickly. Golden ratio scaling in land-based vehicles. We're moving from the ocean now to the land, and we're going to see that the speeds have picked up, obviously, in general, from waterborne craft, and we're going to be able to see this geometry in a little bit more graphic detail here. It's a lot more visible. So this is just an example of a sports car. We've got a number of these to look at, but you can see the wind tunnel testing that's gone on this automobile. You can see the laminar flow. So the geometry of this car is fairly good from an aerodynamic perspective. And we're going to see that in land-based vehicles, for the most part, we're not going to see the 27,309. We're going to see the 13.654. And that's because you don't want to be pushing air down onto the ground from the bottom of the vehicle, unlike in the air where it maybe doesn't matter unless you have a jet engine underneath you. Here we have to keep the car on the road, and the vehicle would be subjected to a lot of flutter and instability if you were to aerodynamically, approach the bottom of the vehicle with aerodynamics as well. So this is just an example. Here's some of the things we're going to be looking at. Some of these will be obvious and some of them won't be. Even soapbox derby racers from back in the day have this geometry. 1940s and 50s concept cars, Indy racers, Formula One racers, drag racers, sports cars, bullet trains, and land speed record holding vehicles. So we've got a lot to look at. So let's get started. Here's some examples of some older soapbox derby racers. You can see here that the GRS geometry shows up in these examples. Here's another one, and you can see that somebody in the family, parents are allowed to help. I checked that out on the soapbox derby design. So I guess mom and dad were able, some of them were engineers because they knew this geometry. This is the 1948 Tucker torpedo. You may remember we discussed Secondo Campini, who designed the second jet airplane in the world. And he was heavily involved in working with the Tucker torpedo. This was a company directly after World War II. Very futuristic design here with this geometry showing up in the front, and probably shows up in the back as well. But this is just an example of how people were taken with the geometry of aerospace and so forth after World War II. Actually, the fenders on these cars would go come out, on turns and so forth. It was very futuristic, but the company folded in 1948. But anyway, there's an example of a futuristic car design using Golden ratio scaling. Now, this is a 1958 Plymouth Tornado concept car. Similar idea. You see the nose cone here, which is identical, has this geometry down pat. So they were just reflecting the geometric design of the space age that was coming to the fore, and replicated it in the automobile industry. Now we're going to look at some real, sports cars from contemporary times. And what you're going to find this geometry in both the front and the rears of the cars. It's a little harder to measure it in the front a lot of times because the headlights are blocking your view of seeing the front of the hood very well. But there are some circumstances and situations where I was able to get the front half of the car as well. So this is a Ferrari F40. You can see in the back of the vehicle, we've got the 13.654 geometry. Here, I've got the same car, and we can see it relatively well in the hood here because we don't have any headlights in the way. This is a Ferrari FXXK EVO. Not a sports car enthusiast, but looks like a pretty fast car to me. And you see that here in the rear, very, very prominent geometry. And here you can see it as well in the hood of the Ferrari as well. This is a Lykan Hypersport automobile. This is a custom manufacturer, I think, in Houston. But you can see this in the rear, and you can also see it here in the front of the automobile as well. McLaren GT, you can see it very clearly in the rear, and you can see it to some extent in the front as well. There's always this pesky problem of the front windshield that keeps most of these cars from having the best possible aerodynamics because it just doesn't make sense to limit the inside room of these automobiles on the margin just for a marginal increase in aerodynamics. But this is the front of the McLaren. Here's a Porsche 911 concept vehicle I saw. Perfect geometry in the back. And this car, you can see probably the best, the aerodynamics of this car going from the very base. You have to kind of visualize it through the headlight, but you can see that the geometry actually of the windshield seems to conform quite well in this case. And here's the Renault Desire in the rear and also in the front of the car as well. So now we'll move on to true racing cars. And we're going to look at some Indy racers. We're going to see the golden ratio scaling geometry in the front of this Indy racer. And here's another one. And you can see it's virtually identical. Now we'll see some side views. You can see it in two different places on the Indy cars. You can see it in the front, and then you can also see there's essentially like spoilers in front of the rear tires, and they have this geometry as well. So we see it in multiple places. Here's another Indy car with the same demonstrating the same geometry as well. Now, this is a Formula One car, and once again, you see the geometry showing up in the front of the vehicle. Here's another shot of a Formula One car's front end with this geometry. And here's a side view, once again demonstrating that as well. Here's another Formula One racer from the side with exactly the same geometry. Here are a couple of dragsters. You can see here and this dragster as well. They both, share this geometric angle, so you'll find it in dragsters as well. Now we're going to move on to bullet trains. This is a really amazing demonstration as well. Trains in the United States have not really caught up with bullet trains, the rest of the world, but here is the fastest train on the planet, which is the SC Maglev in Japan. It'll go 603 kilometers per hour. You can see here clearly the 13,654 angle showing up in the front car of this train. This is another Japanese train, goes 320 kilometers an hour. It's the JR 500 Labyrinth. Has this geometry as well. Here's a Spanish train, the AVE Renfe, and it has the geometry as well in front. Here's another Japanese Shinkansen E5, goes 360 kilometers per hour, has this geometry. And also the Shinkansen N700, which goes 362 kilometers an hour. So everywhere we look in bullet trains, we're finding this geometry. And finally, to get to the fastest land speed vehicles on the planet, we're going to look at a couple of the land speed record vehicles that have set various types of records, usually at the Bonneville Salt Flats. But this is the Bloodhound SSC, and we see the 13.654 geometry there in the front. This is an older craft called the North American Eagle, and you'll see it still incorporates the 27309. I'm not sure why they chose to do that. Maybe the vehicle was so heavy that they didn't need to worry about flutter, but you still see GRS in that as well. And here's another land speed vehicle with the 27309. Interestingly enough, it does have the base of the vehicle is flattened, so you're getting that downward push in that vehicle as well. And here's probably the most classic, the one that I grew up knowing about, which was the Spirit of America, Craig Breedlove. This was, I think, back around the 1970s. So older version, classic, but you see the 27309 golden ratio scaling geometry in that vehicle as well. And finally, the Thrust SSC, I believe this is the fastest one that I have seen in this group. And you can see the 13,654 geometry in the front as well. So clearly, now that we're into land vehicles, we're going faster. We see this geometric angle, particularly in the rears of vehicles such as the sports cars, but you'll see it in the front end in the really rapid, fast cars that are not going to be turning, but are just built purely for speed. It's going to show up in the front. Starting with this section on munitions, we're now going to be looking at things that fly through the air. So we're going to start to see this geometry more and more precisely in these objects. The first thing we want to look at are munitions. Here's an example of a bullet, traveling through the air. And this bullet has the golden ratio scaling geometry in it. We showed this earlier. This is it's called the 8mm Mauser bullet. This was used as the basis for the V2 rocket, which was the basis for all modern aerodynamics. So this is a very important concept to catch, that all of these bullets have golden ratio scaling in them. And that's probably this is perhaps the purest form of example that we can find that golden ratio scaling is clearly the preferred geometry for speed and for laminar flow. So here's another bullet that I took a picture of and measured. Here I measured the back of the bullet as well. This just shows that this is kind of follows the Sears Hawk body, in the sense that the back end of it has the same angle geometry, only in reverse, as the front of the bullet has. And here's another example. All of these bullets have the same geometry. And it doesn't matter if we move into larger types of artillery shells. These are 105 millimeter artillery shells. They have this geometry. And here, the 155 millimeter artillery shells we've been hearing a lot about in the context of the situation in Ukraine, but they all have it as well. So all of the artillery, whether it's a bullet or a big piece of artillery, are going to have this geometry. Now we'll move on to lighter than air vehicles. This is a picture of the classic Goodyear blimp that goes around the country, or used to, and played at football games and so forth. You can see its geometry is very, very close to both, number one, the Sears Hawk body that we see, in the upper left-hand portion of the diagram, as well as the Japanese cave drawing that we found of this, space vehicle that was in the cave in Japan. So you'll see here in the front, you see this geometry. It's a little bit easier to see it in the rear. But the Goldden ratio scaling geometry is in the modern day, Goodyear blimps. We're going to go back in time and look at some other dirigibles. This is the famous Hindenburg from Germany, and you can see the geometry there very clearly in the rear of the craft. Now here's another lighter than air vehicle that was manufactured in Great Britain. It's the R-38 class airship, and you see it there as well. Here's one of the U.S. Navy's dirigibles, the USS Akron, that has this geometry. Here's the USS Los Angeles, has it as well. And now, just to finish up, I wanted to show you a few examples. I was on YouTube and I thought it would be a cool idea to see if they had some articles on the best flying paper airplanes. And sure enough, when you look at the top paper airplane designs, here's one of them, has this geometry to it. Here's a very elaborate paper airplane with the geometry in the front. And here's another one. This one was reported on YouTube as being the best long distance airplane. And you can see it has the 27309 geometry. And finally, we've got the this airplane, which I believe was touted as flying the furthest distance. And this has the 13.654 geometric angle. Goldden ratio scaling and private jets. In this section, we're going to look at private jet aircraft on the market. We're going to look at a sampling of all the different manufacturers from around the world. And then we're going to do the same thing with commercial jet aircraft as well. So we're going to be finding, as we have said before, the Goldden ratio scaling geometry in both the front and the rear of the aircraft. And again, this is very much in keeping with the Sears Hawk model that we've discussed previously. So we're going to start with the Bombardier. This is the Challenger 350. This is a Canadian aircraft, and we're looking at the front of the craft, and we see the Goldden ratio scaling geometry there, and we see it as well in the design of the rear of the craft as well. So it's fascinating to see. And then here's a Cessna. We see the geometry in the front of the aircraft as well as in the rear. This is a model that is not yet out. It's due out in 2025. Dassault Falcon 6X. We'll see this in the front of the aircraft as well as in the rear of the aircraft as well. This is Embraer. This is a Brazilian private airplane manufacturing company. This is the Legacy 500. We see it in the front and in the rear of the aircraft. And this is Gulfstream G280, a U.S. manufacturer. And again, we see the geometry in the front and in the rear of the aircraft. Now, we have many, many more examples in the appendix. I have every model of private jet aircraft that's been built, and you can look at each and every one of the examples in the appendix. Now we're going to move on to commercial aircraft, and we're going to be finding golden ratio scaling here as well. So I took one example of each major manufacturer. This is an Airbus 220. We see the geometry in the rear of the airplane. I found blueprints of all of these as well, so I was able to measure from the top views. We see this in the front of the aircraft as well as in the rear. And then I took an example from Boeing. This is a Boeing 737. We'll see this in the rear of the aircraft here. And in blueprints, we can see it in the front from the top perspective, as well as in the rear of the craft as well. This is a Bombardier aircraft, the CS-100 from Canada. Again, we see it in the rear from the side view. We see it in the rear from the top, as well as we see it in the front of the craft from the top view as well. This aircraft is a Comac ARJ21 from China. Again, we see it in the rear of the craft, as well from the top view in the front and in the rear of the plane as well. This is an Embraer E-Jet 2 E2 from Brazil. And again, we see it in the rear, we see it in the front, and in the rear from the top view. And there are plenty more examples of these. Again, every single commercial airplane I've looked at, jet aircraft, and all of those measurements are available in the appendix. The next area we're going to explore is the area of golden ratio scaling in supersonic aircraft. To review, a supersonic aircraft is any aircraft that flies over the speed of sound, or Mach 1. That's the definition. So as you get into supersonic aircraft, the engine that is used is drastically different in its design than a traditional jet turbine engine. We'll be talking about that later a little bit, but this is an example on this cover page of the Soviet Tu-144 SST that was developed back in the 1960s and 70s. I think it was ultimately dropped, as was Boeing's. We'll see in a few minutes. But what this picture depicts, though, you see these the jet engines, unlike in a traditional commercial airplane with jet turbine engines, these engines suck in air at a very fast, while it's flying very rapidly. And this is most likely some type of a Ramjet or Scramjet engine that is in this vehicle. And so the reason why that's important, you're going to see as we proceed that the nose of the supersonic airplanes they have flat bottoms, and the reason for that is to not disturb the airflow, and make it turbulent as it goes into the intake areas for the jet engine, the Ramjet engine. So we're going to start. This is a more recent aircraft. This is an Aerion AS2 business jet, but it flies at supersonic speeds. You see again, the bottom of the nose of the airplane is flat, and you only see the angle on the top, and that's the 13,654 geometry. This is the original SST that was done both as a joint venture between the British and the French, and you see there the 13,654 geometry. And you see how again, the engines are below the main wing of the aircraft rather than being uh, uh, above it or, at the same location. So that's the reason why you don't see, you see a flat underside to the nose. And here we see this 13654 geometry in the rear of the vehicle as well. This is the Boeing craft I was referring to earlier. This is the Boeing 2707 SST. It was abandoned in 1971. I believe that had to do in large part with regulations that came into effect in the U.S. that outlawed, sonic booms, and that basically rendered, this as an obsolete and failed project at the time. And here's an example of the Boeing in the rear. You see the 13654 geometry there as well. This is a new technology. Boom Technology is a new company that is exploring ways of being able to have supersonic transport, I believe without sonic booms. I believe this is the company, but you can see in their test vehicle, which is due out in about 5 years, that they have this geometry in the front end as well. And this is another version, a two-engine version of their commercial airliner that's they're in development on. And you can see that the rear has this geometry as well. Now this was done some time ago. This is from Lockheed Skunk Works. It's called the Speed Racer. We see the geometry there as well as in the rear of this vehicle. Here's another SST vehicle that's in final stages. It's the Spike S512 QSJ, due out in 2025. We see that geometry in the front as well. Here's another plane from Russia. This is the Sukhoi Su-75 Checkmate. And, we're getting into, this is a military craft, but you can see that this geometry is showing up distinctly in the front end of the Sukhoi Su-75. And here is a side view from a blueprint, and you can see the 13654 geometry in the tail of the craft as well. Here's a vehicle from the TAI Con TFX, which is being made in Turkey. It's under development, due out in 2028. And you see the Goldden ratio geometry there. Here is the Tupolev Tu-144 that we talked about that was on the cover of this section. And you see the 13654 geometry there, as well as in the rear of the aircraft. Now we're going to talk about this in airfoils. Now, for those who are not familiar, as I wasn't when I started, an airfoil, this research, an airfoil is a streamlined body that is capable of generating significantly more lift than drag. Wings, sails, and propeller blades are examples of airfoils. And we've seen this in sails very early on in the presentation. Propeller blades, we're going to be talking about those very shortly. So aerodynamic force can be resolved into two components, lift and drag. The lift of on an airfoil is primarily the result of its angle of attack. Airfoils can be designed for use at different speeds by modifying their geometry. Those for subsonic flight generally have a rounded leading edge, while those designed for supersonic flight tend to be slimmer with a sharp leading edge. All have a sharp trailing edge. So let's see what airfoils are all about. To begin with, I found these two examples of airfoils in single engine prop planes. Why is that important? Because they're fixed and there's no, it's easy to measure these angles to give you perspective. So in the back of the aircraft, we see the 13654 angle. And in the front, we have the 27309, but both Goldden ratio scaling angles. And here's another example demonstrating exactly the same thing. This is a private airplane called the Symphony. And now, as I say, it's challenging to do this, but I researched extensively and I did find one airfoil example of a major commercial airplane online, and that's for the Boeing 737. Now you can see here that there's a lot of different geometries. It's variable in the back, or in the front, but in the back it's basically identical. So, again, we see the 13,654 angle showing up in the rear, or excuse me, in the airfoil. Now here are a number of diagrams that are on the internet. They didn't come with any specific allocation to a particular plane or wing on an airplane. But what's interesting is that all of these end up having this geometry, no matter, what the diagram could have, may be. So we're seeing this very clearly in these airfoil diagrams, no matter where we look. So, well, this is another example of airfoils. Now we're going to look now at the helicopter blade airfoil that I mentioned earlier. This is a cutaway of a helicopter blade, and sure enough, the leading edge once again has this 27309 geometry, Goldden ratio scaling, and the trailing edge has the 13,654. So we're seeing these Goldden ratios everywhere in airfoils. Now I'm on to the section of angle of attack. This is a particularly challenging one to try to measure because it's hard to know the angle of attack on an airplane when it's in flight and to measure it. But I did find any number of diagrams, again, on the internet describing angle of attack. And it seems as though this 13,654 number is showing up as well as it should in theory, because if that's the proper angle for it for a bullet train or a bullet or any other aerodynamic vehicle, this would be the proper way, the most efficient way to attack the air in front of it from a sacred geometry and aerodynamic standpoint. So there's one example. We'll see it here again. I just took examples off of the internet to show that this angle of attack seems to be the 13,654 in all cases. Here's another example showing airplane line of attack. And what's of interest is we'll see that the line of attack here exactly matches the angle of the airplane itself, which is 13.654 degrees. So here's another example of the angle of attack. And another, all of these examples, I didn't cherry pick these. They were all on the internet and I measured them and they all seem to have this angle. Now we're going to look at an area called Vortex Generators. And a vortex generator is an aerodynamic device consisting of small vanes, usually attached to a lifting surface, such as an airplane wing or an airfoil, or a rotor blade of a wind turbine or a helicopter, potentially. When the airfoil is in motion relative to the air, the vortex generator creates a vortex which delays local flow separation and aerodynamic stalling, thereby improving the effectiveness of wings and control surfaces such as flaps, elevators, ailerons, and rudders. Now we're going to talk about a few of these, but let's see exactly what this is all about. If you've been on an airplane before and you sat near the wing, you've probably seen these things on the aircraft and wondered what they were. Well, these are the vortex generators that we're talking about. And interestingly enough, the angle seems to occur at 27.309 degrees. Now, why are these important? You can see here, this is a wind tunnel experiment. On the left is a section of an airplane wing without vortex generators on it. And on the right side, they are included, and you can see how smoothly the air is flowing aerodynamically once the vortex generators are in place. And here's an example in real lifetime. You can, it may be hard to see, but there are these vortex generators right up here, and they are managing to keep the air flowing in laminar flow, and as you can see, it's hugging the shape of the airplane wing, and that's the desired effect to achieve these effects that we discussed a moment ago. Here's another one. It looks like with a 13654 geometry on it. These are tough sometimes to measure because of the picture quality. But here's another example of the Goldden ratio scaling geometry in the vortex generators. And here's another one on another airplane with the 27309 geometry. These are actually vortex generators for automobiles, and these will generally be seen on the back, directly underneath the back window, the rear window on the car, and they have this geometric angle as well. So you can see it here both in the vertical angle of attack and also in the horizontal as well. So these devices are called Vortilons, which stands for vortex generating pylon. Now these are located under the wings and are used to improve handling at low speeds. And again, we see this very same Goldden ratio scaling geometry showing up in these Vortilons. The next section we're going to discuss, we're getting into the really fast aircraft now, are the world's fastest aircraft. And you're going to be surprised perhaps to find out that some of the world's fastest aircraft were actually developed immediately after World War II in the 50s, 60s, and 70s. We're going to start with some of the slower ones, but this is the North American XB-70 Valkyrie, which had a speed of 3.2, or Mach 3.2, and it was developed in the 1950s. And we see that in the front end of this Valkyrie vehicle. This is the Bell X-2 Starbuster, and it's one of still the 10 fastest craft ever, developed in 1945, either at or at the end of World War II. So it has it. This is the MiG-25, which was developed in 1964. It has the same geometry. And here we see it from the top view in the blueprint. And this is the Lockheed YF-12, again, developed in the US back in 1963. It had a maximum speed of Mach 3.35. We see that geometric angle there as well. Here's another picture of other parts of the front end of the jet engines display this geometry, as well as here's a top view of the front of the craft as well. This is the SR-71 Blackbird, Mach 3.35, done in 1966, and it has this geometry in the front. And this is the X-15, which achieved Mach 6.7 in the 1960s. Again, we see that geometry in the front. This section, we're going to talk about golden ratio scaling in spacecraft. We'll start off with the U.S. Space Shuttle Challenger. This was developed and first flown in 1983, designed by Wernher von Braun and his team from Germany. And as we're going to see in this section, we're going to see examples of both U.S. Post-World War II spacecraft as well as those of the Soviet Union. And of course, what we're going to find is that golden ratio scaling shows up in all of these um, uh, ships and spacecraft. And that's not a surprise because we saw, even if we're not sure that uh, they used this precise methodology to get there, they used the same basic geometry, in Nazi Germany. So we'll start here with the Space Shuttle Challenger. I'm going to show you as well a blueprint. Blueprints are always my preferred way of measuring because they're the most precise way for me to measure. But we can see that in the photograph in the previous page, we saw the 76,345 geometry. We measured it with the 27,309, which is actually a little bit more accurate because you can see the angles, much more precisely this way. But anyway, golden ratio scaling is showing up in the space shuttle. Here's some rockets that were also developed by the German scientists who came over. This is the Jupiter PGM-19 rocket, and as you notice, the nose cone of this rocket has the golden ratio scaling geometry as well. I more recently was able to find a blueprint of the nose cone as well, and it fits perfectly. Here is the Soyuz capsule. This is used by the Soviet Union to transport people to the International Space Station. And here again, we see the golden ratio scaling in that piece of in that spacecraft as well. This is the Sputnik 2 capsule from the Soviet Union, and this was flown, in the early days of the space program. It has the golden ratio scaling in its geometry as well. Here's the Sputnik 3 capsule from the Soviet Union, and here again we have a blueprint, which is my preferred way of measuring, and the golden ratio scaling shows up perfectly in the geometry of the Sputnik 3 as well. Also shows up in the SpaceX Dragon, Elon Musk's firm. And here we see it. This is called the ISRO RLV-TD. This is actually the India equivalent of our space shuttle, and it has this geometry as well. Here is the re-entry vent vehicle from the Titan II. This allowed for manned, suborbital spacecraft in 1963 with this geometry as well. And here is a satellite, WRE-SAT satellite from Australia, which went into low Earth orbit. And we can see here, once again, just a perfect match of the golden ratio scaling geometry in this satellite as well. And then finally, we'll end up with the Redstone rocket. This again was another von Braun inspired rocket geometry design, and we see the golden ratio scaling here as well. In this section, we're going to explore golden ratio scaling in missiles. Now, missiles, we've studied and looked at bullets before, and we saw that they were a perfect match. In many respects, at least the front end of a missile is virtually identical to that of a bullet. Both of these devices are meant for speed and stability. And sure enough, we find golden ratio scaling in the nose cones of every missile that has ever been manufactured in the modern era. So, we're just going to go through a few examples here, show you that it's not just the United States, China, India, Iran, that and Russia that have this geometry, but it's known throughout the world. So uh, we're just going to start with the Abdali 1 missile from Pakistan. You see here, this is an experimental, I believe, vehicle of some sort. The ADM-160 MALD from the United States has this geometry. This is the AGM-158 manufactured in the United States as well, showing this geometry in the nose cone. And this is actually the AGM-183A ARRM. Now, why is this important? It's important because this is the delivery system that's been put together for the, at least to date, unsuccessful U.S. hypersonic glide vehicle program. So, but you can see that the nose cone in which the hypersonic glide vehicle will reside, it does have this geometry. So, we're going to be talking a lot more about hypersonic glide vehicles later in the documentary. And here's one from India, the Akash NG rocket. And here's one from Iraq, the Al Hussein missile from Iraq. Here's one from the UK. This is called the Black Arrow. It was the United Kingdom's first missile. And here is the BrahMos. This is the world's fastest cruise missile, and we see the geometry in the nose cone there as well. Here is the Fateh 110, which is an Iranian missile system containing this geometry. And here is the GAM-87 Skybolt from the United States. This is a little older rocket. Here's the GLL-31 rocket from Russia. I'm just taking samples from all countries, all eras here. The Hwasong-13 from North Korea. This is the Khalij Fars from Iran. The Pershing 2 missile from the United States. And here's another one from Russia, the R-36 missile from Russia. Now in the appendix, I've got a complete listing of the examples of golden ratio scaling, and I used the Wikipedia list, so I think I pretty much got everything, but it's virtually all military missiles that have ever been developed since World War II. So every one of these has golden ratio scaling in its geometry. So this is definitely a universal phenomenon. The next area we're going to explore is golden ratio scaling in jet and rocket engine nozzles. Now, this is important because this is going to demonstrate, as we discussed at the beginning of the documentary, implosion and explosion geometries are identical to each other. It's just the directionality that changes. And we're going to see that very phenomenon here. As it turns out, golden ratio scaling is the key to maximizing thrust in jet and rocket engine nozzles. So to start with, I want to get some basic concepts down as to what a nozzle is. This is me when I was 4 years old. I wish I never looked that good, and I don't think they had color photography those days. But anyway, here's a young boy who's squirting the nozzle of his hose with his finger, and he could be using a nozzle like the one on the right as well. But all of us have played around with the hose when we were little kids and loved to see how far we could spray the water. And we realized very quickly that the more we could cover the hole on that nozzle of the hose, the further that was going to spray out. And that's really, in short verse, the definition of Bernoulli's principle and Bernoulli's equation, which we're going to get to here. So, here is Bernoulli's equation. We're not going to do the math on it, but basically for a liquid, and this is important, what we just saw in the previous, these equations demonstrate what we just found in this photo, namely that if we minimize the volume that water can escape through, it's going to squirt a lot further. And the reason for that in fluid dynamics is due to these equations in Bernoulli's equations. Now, this works fine with hydrodynamics, or in other words, anything like water that's essentially incompressible. Then these basic equations and relationships hold true. But once we get into gases, we're going to find that that's not the case. So this is, I'll tell you where you can get more information to learn more about this, but this is a diagram from a documentary that was done about 10 years ago by the Hypersonic Research Department at the University of Queensland in Australia. And why I like this, we can leave the numbers out for a minute because all I really want to do is look at directionality for this purpose. If we look over in the left-hand column, we have geometry, and we see a nozzle, this is called a divergent nozzle. In the top example, which is a divergent nozzle is one that goes, it increases its diameter from the point where the air enters the conical shape. Now in the bottom, this is called a convergent nozzle. So divergent and convergent are the two concepts here. We'll talk about those in a minute. Well, what's fascinating is that when you have a divergent nozzle, or geometry, such as on the left, top left, that acts as a nozzle for supersonic vehicles, meaning those that go over Mach 1. And for those objects that are going at less than Mach 1, it becomes a diffuser. Now, what would a diffuser be? It's just something that dissipates, actually, the thrust rather than maximizing it. Now, when we look at the convergent nozzle down at the bottom, we see just the opposite happens. So at subsonic speeds, it acts as a nozzle, just like our water example a minute ago, but it acts as a diffuser at supersonic levels or speeds faster than Mach 1. So that's the key concept. And it's an amazing, counterintuitive one, but we're going to see that it holds true. So here's an example of the power of gaseous explosion. I saw this video, and you can find this at Get a Class Physics on YouTube. They did this video where they demonstrated the power of gaseous explosion that's received a tremendous amount of kinetic energy, in this case, due to a nozzle shrinking in size and then expanding again. So that's where the kinetic energy is derived from, is from the compression of the air. And in this case, the experimenter is blowing in, I think they took two plastic champagne glasses and put them together, and that's what they came up with. But he's blowing through this tube air, and as it's coming out the other side, you can see that he's hooked this other tube into the exiting champagne glass. And what you see below, this is a glass of colored water with dye, and you can see how much pressure is being developed, that it can suck the water up that far just from the suction coming out of this system from his breath alone. Now, here's another example that they demonstrate, and you'll notice the geometry of this champagne glass. It isn't quite right, but it's real close to our optimum geometry of Goldden ratio scaling. And you can, in this example, they've got a fan that's blowing air into the tube rather than a human being. And we can see that with enough pressure, it can this effect will literally suck the air out of this plastic bottle. So tremendous pressures here, and so we can see why geometry is very, very important in getting thrust out of these high-speed vehicles. Now, if you're interested in learning more about this, I found this a series of lectures. It's called Hypersonic Aerodynamics Explained. It was done, as I say, 10, 12 years ago by the Hypersonics Department at the University of Queensland, Australia. It's a real good way to, if for those interested in learning more about hypersonics, they go through all the math, which we're not going to try to do today, but it's an excellent source of information on hypersonic aerodynamics. So now I want to start talking about nozzles and tell you a little bit about Gustav de Laval. He was a Swedish engineer and inventor who made important contributions to the design of steam turbines. In 1890, Laval developed a nozzle to increase the steam jet to supersonic speed, working from the kinetic energy of the steam, just like we were doing in those previous examples with compressed air. That was so the nozzle, now known as the de Laval nozzle, is used in modern rocket engine nozzles. So here's a couple of diagrams that discuss this. The nozzle is a convergent, divergent, or CD nozzle. And again, we're going to go through that on the bottom left here. You can see how the front half or the inlet of the nozzle is converging, but after it gets to this middle area called the throat, which is the smallest part of the stream, you can see that it diverges again. And in this example, it's using Goldden ratio scaling, but we'll see it in real life here in a few minutes. But the nozzle is a tube which is pinched in the middle, making a carefully balanced asymmetric hourglass shape. It's used to accelerate a compressible fluid, that like the air, to supersonic speeds in the axial direction of the thrust by converting the thermal energy of the flow into kinetic energy. De Laval nozzles are widely used in steam turbines and rocket engine nozzles. It also sees use in supersonic jet engines. Laval's convergent divergent nozzle was first applied to a rocket engine by Robert Goddard, and we saw his design earlier. So this is just a simple diagram showing you the structural components of a jet engine, a ramjet engine, and a scramjet engine. And you can see there's a compression phase, there's a combustion phase, and an expansion phase. Now, with respect to the expansion phase in a jet engine, that is one that goes below Mach 1. We can see that in the expansion phase, the nozzle is in a convergent shape, which is what we learned from the folks at the University of Queensland a minute ago. But when we're using supersonic and hypersonic engine design, we can see that we have divergent nozzles in the expansion phase of the nozzle design. So how do nozzles create thrust? A nozzle helps to define the exit pressure of the combustion gases to ambient pressure. And if the combustion gases have enough pressure to be accelerated to supersonic speed, which a ramjet and scramjet engine have by definition, the nozzle is actually first convergent and then divergent to achieve the best acceleration of the flow. The convergent subsonic flow accelerates, until in the section with the smallest area called the throat, the speed of sound is reached and the following divergent section accelerates the now supersonic flow further until its pressure drops to ambient pressure. So let's take look at some examples. First in jet engines, and these are all older jet engines. And the reason we know that is because they have a fixed subsonic nozzle. These fixed nozzles were used in the early days of jet engine design, but it's most evident in these nozzles that we can see the Goldden ratio scaling. So this is an Allison J35 fixed subsonic nozzle with the Goldden ratio geometry. Here's another one. This is an Armstrong Siddeley Viper with a fixed subsonic nozzle with the Goldden ratio scaling. Aviad Digital PD14. This is a Russian fixed subsonic nozzle with this geometry. And there are many more like this that I could have shown, but I now want to show you what are called variable nozzles. And variable nozzles are found usually on military aircraft, and they're usually found in conjunction with what's called an afterburner. An afterburner can be located between the exhaust, the initial exhaust of the engine, and where it ultimately comes out the rear of the jet airplane. They take that hot exhaust and they reburn it by putting in additional fuel. Now, when that's occurring, generally this shape that I'm showing here does not exist. In fact, this geometry is more for aerodynamics because at this point, the nozzle is actually coming out straight. But if they're using an afterburner to go above Mach 1, we're going to see that flare out, and the geometry of the nozzle becomes divergent rather than convergent. And we'll see that, on several of these airplanes. This is an airplane from South Korea with a variable nozzle, and Lockheed F-161, which is from Israel, joint developed with Lockheed. So those are variable nozzles, but what's again of interest right now is that they aerodynamically designed the exterior of these nozzles to conform to the Goldden ratio scaling geometry. Now we're going to talk about rocket engine nozzles. We saw this earlier. Robert Peltery was the first person that I saw that designed a rocket engine nozzle prior to the V2 rocket, but he knew of this geometry. But let's do a little introduction here. Jets, ramjets, scramjets, and rockets use nozzles to accelerate hot exhaust to produce thrust. The amount of thrust produced by the engine depends on the mass flow rate through the engine, the exit velocity of the flow, and the pressure at the exit of the engine. The values of these three flow variables are all determined by the nozzle design. Ramjets and rockets typically use a fixed convergent section followed by a fixed divergent section for the design of the nozzle. This nozzle configuration is called, as we've said before, a convergent divergent or CD nozzle. In a CD nozzle, the hot exhaust leaves the combustion chamber and converges down to the minimum area or throat of the nozzle. Expansion of a supersonic flow causes the static pressure and temperature to decrease from the throat to the exit, so the amount of the expansion also determines the exit pressure and temperature. The exit temperature determines the exit speed of sound, which determines the exit velocity. The exit velocity, pressure, and mass flow through the nozzle determine the amount of thrust produced by the nozzle. So let's look at, with that as background, We saw this earlier, but now let's look at the geometry of the V2 rocket nozzle that was developed by Wernher von Braun. And we can see again on the left, here's just a simple picture that I measured of the nozzle on the bottom of the V2 rocket. But on the right, and these are always the preferred method for me, when I can find a blueprint and I can measure it so precisely, I know that I'm spot on. And so we see the Goldden ratio scaling just fits perfectly inside the exhaust nozzle of the V2 rocket. Now, as you may recall from other sections, after World War II, of course, German scientists who worked on the Nazi military rocketry program were kind of split between the Soviet Union and the United States. So it's not a surprise to find this same geometry in the rocket nozzles that came from the Soviet Union and from the United States. So this is the 8K 72K Vostok nozzle. This was used on the Vostok rockets in the early days of the Russian space program, and it has the Goldden ratio scaling geometry. This is the Armstrong-Siddeley Stentor rocket engine. This was developed in the UK. And once again, we see this geometry. Again, not a surprise for the UK because the UK took a number of the V2 rockets after World War II, and they jointly explored that with even Russian scientists in the early days after World War II and US scientists. And they were able to retrofit and re-engineer, just as I've done with the Russian pyramids, the geometries that were found in the V2 rockets. So here we see another example of this. This is called the Blue Streak, again from the United Kingdom. You see the rocket engines have this fixed nozzle design with Goldden ratio scaling. Here's a Russian design, Boron Energia PA301, which has this geometric angle. Here's a rocket booster engine design from the Navajo rockets, which were used in the early days of the U.S. Rocket and space program, Goldden ratio scaling. And this is another Russian rocket, the RD-107, and followed up by the RD-110. And if you start to notice, I still call this a fixed nozzle design, but you're going to start to notice here that the bottom of this has Goldden ratio scaling, but as we get up towards the top, we're starting to see a little bit of change in the geometry. And this is kind of a transition point, but we'll get to the variable nozzles here in just a moment. And here's the UR200 has the fixed nozzle design as well from Russia. And here is the RS-25. This is the rocket designed by Wernher von Braun and others from Germany to power the U.S. space shuttle. And once again, as I was mentioning, you can see it's got the Goldden ratio scaling geometry just up until the last part of the top of the nozzle when it gets to be a little bit steeper. Now we're going to talk about bell nozzle designs. We started to see this changing in the last couple of slides here, but the bell nozzle design became popular, sometime in the latter part of the 20th century. And essentially, even though we see the Goldden ratio scaling still geometry in the bottom, there was a steeper angle that was used in the top half. And in effect, there were two pieces that were put together, and it created what appeared to be, from the outside, a bell nozzle design. And so that's what it's called. So we'll see that, this Goldden ratio scaling angle is in the bottom of all of these. The top of the nozzle, the top nozzle angles seem to vary somewhat, and all I could do here was to try to approximate what I believed it was, just by iterating to these top angles. So there seems to have been a little bit of variation and testing of different upper geometries here. This one appears to be 60 degrees, as does the Raptor engine nozzle of SpaceX. This is a Rocketdyne nozzle. It's for the F1. We can see it's a bell nozzle design, but if we look down at the bottom, we can see that from the point where the bottom part of the bell starts to its base, that the Goldden ratio scaling geometry is definitely there. So we're going to see a couple more of these examples. Rocketdyne RS-25, got it in the base, and also in the Rocketdyne RS-68. This particular rocket nozzle design powered Apollo 11 in our space program in the 1960s. Here's the Saturn V rocket design as well, and you can see here what appears to be the Goldden ratio scaling in the bottom, and I've measured this as 44.914 degrees. It could be 45 degrees. It's hard to know without a blueprint, exactly how these were drawn, and unfortunately, most of these don't have a blueprint to go on, but it's very, very clear that rocket engines and jet engine nozzles all demonstrate the use of Goldden ratio scaling to maximize thrust. Now we're going to finish up the section on rocket nozzles and look at Goldden ratio scaling in ramjet and scramjet engines. Now, the rocket nozzles of ramjet and scramjet engines are not all that dissimilar from those from jet engines and rocket engines. They're there to maximize the thrust of the fuel that's been burned in the ignition area of the engine, and so the geometry that's associated with them is going to be reflective of that which will maximize thrust through their system. So we've seen this this diagram in a slightly different version earlier. I just wanted to go through kind of what the differences are between jet engine flight speeds, ramjet, and scramjet. So a jet engine will go from a standing start, like a commercial or a private jet airplane or a military jet, and can fly with a traditional jet engine anywhere from 0 up to about Mach 3. So after you get past that, some I think have gotten up to 3.5, but that's basically going to be the limit on a traditional jet engine. Now, a ramjet engine can actually go from about Mach 1 up to Mach 4. This engine is sort of an intermediate, obviously, in speed. One of the key elements of both ramjet and scramjet engines are that in the absence of a traditional jet engine added into the system, or some other way that the missile is going to be able to achieve, a given speed beforehand, ramjet and scramjet engines need that in order for them to ignite. In a ramjet situation, it has to be over Mach 1, and a scramjet engine, it's anything over Mach 1 will work as well. But a ramjet engine is distinguished from a scramjet engine in one important characteristic. The airflow, even if it's supersonic, is slowed down to about Mach 1, or actually maybe even a little bit below, in order for the ignition system, the fuel, to be able to be burned in a ramjet. Whereas in a scramjet engine, it's supersonic. And so that's actually what this SC is for in front of ramjet, because that's for supersonic uh, speeds. So there's slightly different configurations. In the case of the ramjet engine, it's necessary to get the speed down below, um, um, Mach 1. So the geometry actually of the cone from in the intake side is not going to, it's probably not going to have this geometry of Goldden ratio scaling, although it may show up in the exhaust. Now, similarly, in the scramjet, you may or may not find it in the intake section, but it would be the geometry that would help to maximize laminar flow and probably improve the ignition phase. But in both cases, we could expect to see the Goldden ratio scaling and the cones coming out of the exhaust. So just to review ramjet and scramjet, a ramjet is a jet engine without a compressor or a turbine. It is essentially a tube through which air enters purely as a result of the plane's forward motion. At the inlet, the air hits a diffuser to create high static pressure for combustion and is slowed to subsonic speeds. Fuel is supplied and the fuel-air mixture is burned. The heated gases that result are ejected at the opposite end through the exhaust nozzle. Ramjets, by definition, need ram air, that is to say, air that is forced into the intake as a result of the aircraft's high speed. Thus, they cannot function at low speeds. The acronym Scramjet stands for Supersonic Combustion Ramjet. It is distinguished from the ramjet by the fact that combustion occurs at supersonic air velocity inside the engine. This enables the scramjet to attain higher speeds than a traditional ramjet, which has to reduce the incoming air to subsonic speeds before it enters the combustion chamber. Since the scramjet does not have to decelerate the air as much, the temperatures are much more tolerable for the engine parts and the materials. So let's go on and check out a few ramjet and scramjet engines. This is the only picture of an exhaust system that I was able to find, either in picture form, was a cutout so I could see it, or with blueprints, which don't exist. And I can understand why that would be for, these highly sensitive documents today. But this is a ramjet engine from a company called Reaction Engines. We're going to see later an experimental craft that they're developing called the REL Skylon. REL stands for Reaction Engine, so limited. So that is what we're looking at here. This is a traditional, ramjet design. You've got the cone here in the center, and also you have the exhaust nozzle in the back. Now I've measured the exhaust nozzle in the back, and it measures this perfect Goldden ratio scaling geometry, which we would expect for a fixed nozzle situation. Now the cone in front, however, as you can see, is not equal to 27.309 degrees, and that's because we're trying to slow it down and build up that kinetic energy and heat to assist in the burning process. But you can definitely see the Goldden ratio scaling geometry in the nozzle. Now, when we get into scramjet engines, as I've mentioned, there really isn't anything that I can do here to because they don't exist other than these types of diagrams. What's interesting is that the diagrams tend to indicate that in a scramjet engine, both potentially the front of the diffuser and has this geometry, as well as the exhaust nozzle as well. So you can see two examples here. I'm not going to claim that I know this is a fact, because even though the angles match up, the really key thing, in my view, is shown in this next diagram. We can see this geometry here on the cone, but what I believe is more important is getting this geometry right from the perspective of the ejection of the nozzle. Now here we have a 13.654 degree angle, which would be correct. However, this is still with a divergent nozzles, so I'm not sure that the angles are perfect by any means, but I think that further study of these geometries and their interplays inside the Ramjet and Scramjet engines could produce some significant improvements in combustion. Golden ratio scaling in experimental aircraft. In this section, we'll look at some selected experimental aircraft, both contemporary and back after World War II in the 50s and 60s, when, just as today, there was interest in achieving as fast as speeds as we possibly could. So we're going to look at a combination here because, interestingly enough, there was a pretty long break in time when we, as a planet, we're not really, going after speed as much as we are today. But anyway, this is an aircraft called the Blue Edge from EO Aircraft. It's a U.S. company. It's an experimental craft that is this particular craft is designed as a commercial airliner with a Mach 8 to Mach 10 maximum speed. So quite futuristic in terms of what we have had in the past. So, I think the estimate is that to go halfway around the world is going to take about an hour or something. It's really amazing. So anyway, you see the GRS geometry both at the front and the rear of the craft, and you see the 13654 in the side view of the craft as well. This is the Bristol Siddeley air-breathing booster system. This was, again, a concept aircraft in Great Britain in the 1960s. And we can see here in the blueprint on the right that, the geometry of the craft perfectly matches the Golden ratio scaling. Again, not a surprise necessarily because the British as well as the Russians and the Americans, were able to essentially re-engineer the V2 rocket, and I'm sure found all of this geometric data there. Here's a SST supersonic transport blueprint from Bristol Siddeley, again in the 1960s, and it demonstrates its geometry in its fuselage as well. This is a experimental aircraft, a lifting aircraft or lifting body that was developed in the Soviet Union, and it's called the GLL-8. Hard to find a vertical view or a top view of this, but I did get a side view of this craft, and we can see that it has the 13654 geometry in the side view. This is the Hermes quarter horse experimental craft, estimated to go about Mach 5.5. Again, we see the 13654 geometry, both in the front and in the stabilizer fin at the rear of the craft. And here's a copy of the quarter horse's blueprint, and we can see that the 13654 is built right into the geometry of the fuselage. And in the 1960s, Lockheed developed a manned hypersonic vehicle. That shows you how far back the race for speed originated. And we can see here that the 13654 geometry already was known by the Lockheed engineers and was incorporated into the airplane's design. And here's the Lockheed YF-12 U.S. Air Force designed vehicle, and it achieved Mach 3 plus back in the 1960s. And again, we see the Goldden ratio scaling geometry in the nose cone of the vehicle. This is the M2 F2 experimental lifting body. Again, this was done, I believe, in the 60s. You can see a picture of the craft on the bottom left. And once again, we see the Goldden ratio scaling geometry showing up perfectly in the fuselage and the front part of the craft. This is the Mako hypersonic missile developed by the U.S. Mach 5, and it has this geometry in the nose cone. This is another experimental craft from Martin. That was a predecessor company to Lockheed Martin. It's called the SV-5D. This is called a lifting body experimental craft. You can see a picture of it there on the left. Both the picture of the craft as well as the blueprint demonstrate Goldden ratio scaling. And here's another experimental craft developed by Martin. This one is the X-24B. And we see the front of the craft here has the 13654 geometry. And from the top view, we see the 27309 geometry as well. So all of these old ancient aircraft had this Goldden ratio scaling, and these are among the fastest vehicles on the planet. Here's another example. This is a McDonnell Douglas reconnaissance concept vehicle from the 1960s. It achieved a maximum speed of Mach 6, and we can see that it uses Goldden ratio scaling in its wings and fuselage. This was a McDonnell Douglas manned hypersonic vehicle designed from 1958 with a Mach speed of 4.5. There we see the 13654 geometry as well. And a more recent craft, this is the Sci-Fire hypersonic vehicle, which is a joint venture actually between the United States and Australia. It's been tracked at Mach 5. And here again, perfect match in the geometry of the vehicle with the Goldden ratio scaling. Here's the Sukhoi Su-75 Checkmate. This is another hypersonic vehicle under development by Russia, due out in 2026, and we see that it has the Goldden ratio scaling in it as well. We saw this vehicle a little earlier in the presentation. And here's the rear of the Sukhoi Checkmate, which has the 13.654 ratio geometry as well. Goldden ratio scaling and hypersonic vehicles. We finally gotten to the very fastest vehicles known to mankind. And so this is sort of one of the major culmination points of this documentary. We're going to, as you can see in this cover picture, you see this geometry now, if you're used to visualizing it in all of these aircraft. So let's get started. Just by way of introduction, hypersonic vehicles and weaponry are among the most cutting-edge technologies currently under development by a number of countries, including Russia, China, India, Iran, and the United States. Russia has the technological lead in this area and has developed 3 different delivery systems for hypersonic weapons via airplane, ship, and ICBM systems. Hypersonic travel is defined as travel in excess of 5 times the speed of sound, or Mach 5. Russia claims to have hypersonic weapon systems that travel at Mach 20, or approximately 15,000 miles an hour. Golden ratio scaling is found in every one of the successful vehicles designed for hypersonic travel, as this geometry minimizes friction and drag, reduces heat buildup, and maximizes speed and fuel efficiency. So we're going to look at the 10 fastest hypersonic vehicles in the world right now. And then at the end, we're going to be doing a case study to demonstrate the importance of golden ratio scaling geometry, because we're going to be looking at the Avangard hypersonic vehicle, which actually has been tested at Mach 27, and the US version, the HTV2, which has not had successful outings in its test runs and does not use golden ratio scaling. So let's get going. This is the X-Core Lynx. This is a USA company. This project has now been abandoned, but this vehicle was originally designed to carry, it was a 2-passenger vehicle system that could take off from traditional runways and get up to approximately Mach 5 speed, going into low Earth orbit and returning back to Earth. Now, the project was abandoned in, I believe it was 2018, but this experimental vehicle was tracked at Mach 5. The next vehicle is the Boeing X-51 experimental craft, the Wave Rider. This particular technology uses the shock waves that are generated from supersonic flight to actually help with the lift on the vehicle. But this one achieved 5.1 Mach rating, and you can see the golden ratio scaling geometry showing up in the body of that aircraft. And this is called the REL Skylon. REL is the name of the company. It's Reliance Engines developed this craft, and it's a reusable craft again that uses Ramjet engines and has achieved a speed of Mach 5.4. Now we see the golden ratio scaling in the front of this craft and in the rear here. And also I wanted to show you how much this craft resembles the Sears-Hawk theoretical diagram of the craft with the least possible resistance and drag. So very, very aerodynamically designed aircraft. Moving on, this is the hypersonic glide vehicle. It's called the HSTDV, that's been developed in India and using this geometry, and it achieves Mach 6 speed. This is the SR-72 by Lockheed Martin. This craft is still, I think, in development. It's undergoing various design changes over time, but it has achieved a speed of Mach 6, and we can see the golden ratio scaling geometry in the front of that craft as well. This is the North American X-15. This is another example of these machines that were developed during the early post-war period. I believe this was done in the 1960s. It achieved a speed of Mach 6.7 and has golden ratio scaling in the front. This is the THAAD missile system. This missile system developed by the United States, the missiles can achieve a speed of Mach 8.2, and we can see, we go first to the bottom of the diagram, we see here the tip of the missile inside the system itself, and it has the Goldden ratio geometry in it, as does the rocket engine nozzle that powers it. This is another one of the Russian hypersonic missiles. This is the Zircon, and this is the ship launch system, and it achieves a speed of Mach 9. And here is another version, the Kenzal from Russia. And this is the airplane launch system, and it achieves a speed of Mach 10. This is the Chinese version of a hypersonic glide vehicle. This is the DFZF from China, and it has been successfully tested at Mach 10. And here is another system from Germany. It's called SHEFX, and that's an acronym that stands for Sharp Edge Flight Experiment. What these people are doing at SHEFX is they have decided to redesign missiles and rockets and nose cones and so forth to simplify their construction and cut cost. As you can see, they don't use conical structures. They're using, in this case, I believe it's hexagonal structures to test. And anyway, but they still use this very same geometry. And this vehicle was able to achieve a flight speed of Mach 11. Then finally, we're getting to the fastest vehicle on the planet, and that's the Avangard hypersonic glide vehicle. It's made in Russia. It supposedly has been tested at Mach 27. I was not able to find a diagram for this, a blueprint on the internet, and that's not a surprise, but I did find a number of examples of this, and I took the pictures that gave me the best chance of getting an accurate measurement of its geometry. And you can see here on the right that the Goldden ratio scaling geometry shows up in that picture. I found two more as well, and just thought I'd show you. I've measured those. So, unfortunately, I can't get a blueprint, as I say, but, all of the other pictures that I've been able to find of this craft demonstrate that Goldden ratio scaling is showing up. Now, here's a side view showing, in effect, the vertical angle of attack of the vehicle. And again, we see the 13.654 geometry showing up there as well. So Goldden ratio scaling is definitely being used by the Russians in developing their hypersonic weapons. And now let's take a look at a case study that I put together. And this is the DARPA HTV-2 hypersonic glide vehicle, which you see up in the top left-hand corner. And we're going to look at the angles of attack and analyze those. Now, just by way of background, in 2011, DARPA conducted a test of its unmanned hypersonic glider dubbed Hypersonic Technology Vehicle 2, or HTV-2. The vehicle was able to maintain stable flight for a while at 13,000 miles an hour over the Pacific Ocean. The stable flight lasted 3 minutes before HTV-2's flight safety system plunged it into the ocean. The agency now thinks that unexpectedly large pieces of the hypersonic aircraft skin peeled off. DARPA says that it expected some of the skin to wear down due to the extreme heat and speed of the aircraft. An independent review board has concluded that the most likely cause for the failure was the unexpected aeroshell degradation. Now, I'm going to be showing you some information here, and I'm going to pose the question. The DARPA HTV-2 did not use Goldden ratio scaling in its geometry, and could the lack of Goldden ratio scaling in the geometry be the cause for these problems? So now how do I know that? Well, I went to the source. I found a picture, or excuse me, a blueprint of the geometry of the HTV2 on the internet. And they have different, I'm calling this horizontal angles of attack. You can see that the apex angle on the Avangard is 27.309 degrees. But if you look here on the diagram, we see that we have an angle here of 73.3 degrees at the top. And the point I'm making is without any other compensating design change elements that, we're not aware of, the proper angle here, if we want to compare it to the Avangard and all of the other high speed vehicles that have Goldden ratio scaling, the proper angle here would be 76.345 degrees, which is the bottom side of the triangle that is created by this geometry. So the horizontal angle of attack of the DARPA craft is therefore 33.4 degrees. And how do you get that? You can take 90 minus 76.345 and multiply it by 2, and you get 33.4 rather than the 27.309 degree angle found in the Avangard. So essentially, we're about 7 degrees different from the Avangard and all of the other vehicles in the horizontal angle of attack. Now looking, and this is just a confirmation, I wanted to show you, I did find another version of this vehicle. I think they changed the back of it, as you can see, to some degree. There's different angles in the back here than this model, but the front angle of 33.4 that I found and calculated matches up perfectly. So this angle is about 7 degrees off. Now, if we look at the vertical, we saw on the bottom here, we saw the Avangard before, and we see that the 13.654 degree vertical angle is, very much in keeping with what we would expect. However, the HTV2 blueprint, the vertical angle is way off from 13.654 and isn't even like a half of it. So it's very hard to know where this geometry came from, but I have to ask the question, since we've seen it on all of the other vehicles, is this helping to cause the turbulence and instability that has caused these craft to fail? So all I can say at this point is that given the information that's available on the internet, at least with respect to the HTV2, the geometry that was used in the development of this craft is significantly different than all of the other craft that have achieved these high levels of performance and speed. Now, moving forward, there's not a lot of information about or pictures or blueprints for that matter, of the upcoming successors to the HTV2 in the U.S. arsenal, just as there aren't for the Russians and Chinese and Indians either. So this isn't a surprise, but I did find this picture of the common hypersonic glide vehicle that's under development for both the Army and the Navy at present. And even now, the geometry in the front of the craft seems to be a little bit off compared to the Goldden ratio scaling. So again, I can't say that they haven't compensated for that in some other way, but when all the other countries are using it and there's work and we're not using it and it doesn't work, maybe it's time to look at that. So we'll just keep that in mind as we move forward. Now we'll move on. Since the HTV2 test about a dozen years ago, the government has been working to develop other hypersonic glide vehicles. This one's called the Common Hypersonic Glide Vehicle. It's being developed for both the Army and the Navy. As you can see here, even though the geometry here is very close, it's still not accurate um, uh, in comparison to all of the other uh, high-speed hypersonic vehicles that have been developed in the past. And it would just seem to me that we ought to be asking why, since we knew this geometry in the 1960s and 70s and 50s, why we're not still employing it today, since it works for the other vehicles. Well, we've come to the conclusion of the main part of this documentary. I do want to make a few summary statements and comments before we proceed on. And remember as well that in the appendix that follows these concluding remarks, you're going to find numerous more examples of golden ratio scaling in nature and in the construction of airplanes, missiles, rockets, and the like. So be sure and check that out at your leisure if you want to see even more examples than those presented in the main body. So let's start with a few concluding remarks. Although contemporary fluid dynamics has no way to really quantify or describe the phenomenon that we have discovered today, golden ratio scaling is found in every type of fluid dynamics environment where speed, laminar flow, and stability are paramount. GRS is also the geometry found in engine nozzles to maximize the thrust available from all types of jet, rocket, ramjet, and scramjet engines. This research demonstrates that nature has a preferred pathway of implosion and explosion, which manifests in the geometry of animals, birds, and air, land, and sea-based vehicles. Historical analysis of ancient architecture and flying machines also indicates that GRS has been known about for thousands of years. And yet, despite using GRS in the development of the vehicles developed during the 50s through the 80s, the best publicly available information, which we saw in the previous section, which was the blueprint of the HTV-2 hypersonic glide vehicle, the U.S. hypersonic program is not using GRS in the design of its vehicles, despite the fact that all other hypersonic vehicles that have successfully completed, trips, in one case up to Mach 27 for the Avangard, use this geometry. So this could easily be the reason why the HTV-2 was eventually scrapped, and because of its inability to maintain structural integrity during flight. So much more research to be done on these topics, but by way of just kind of clarifying where I want to go next, there's going to be a lot of other, areas of that I'm going to be researching, but here are some important ones that I want to get involved with quickly. And one of them is to try to at least introduce and integrate the concept of golden ratio scaling into fluid dynamics and computational fluid dynamics. As we've seen, for whatever reason, this information got lost in recent time. We know that as recently as 75, 80 years ago, Victor Schauberger used it, and it certainly looks as though the people who were involved in the German development of the V2 rocket knew it as well. The second is I am quite interested because the Russian pyramid research has indicated that huge ionization fields occur. And now that we've seen that there's actually technology available in the market today for harvesting ions from the atmosphere, my next step is to take a pyramid or any other conical structure that has this geometry and measure the ionization fields produced by it. As you remember, both the Russian pyramid research and the research on the Great Zimbabwe Ruin indicate that this geometry produces high levels of ionization. So if we find that the kind of the artificially induced levels of ionization around a pyramid are such that it could economically produce free energy, that's certainly a topic that I'm interested in learning more about and pursuing. And then finally, I'd like to explore the potential use of golden ratio scaling in nuclear fusion. There are a number of companies out there who are using the concept of implosion in their fusion activities. And we do know, of course, that fusion has occurred, so we know that it's theoretically possible. All we need to do is to change up the calculus to where the amount of energy necessary to create a fusion reaction is less than the energy that's output, and that'll get us over unity. Clearly, geometry, as we've seen from fluid dynamics, is highly important in laminar flow and in both implosion and explosion. So perhaps getting this geometry tested by one of these firms could go a long way in improving, the ultimate results from fusion progress. So these are just a few of the ideas. All of these things are things that we're interested in pursuing. If there are any of you out there, electrical engineers, what have you, that can help us, particularly with the measurement of the ionization fields, we can certainly get access to pyramids to test this on, but we need an expert in that area to help us. And so if there's anybody out there who is hearing this that would like to help with that, same thing with nuclear fusion and with computational fluid dynamics. Anyone in the industry who hears this and would love to hear more about it or to help us with these projects, we're very open and willing to doing that. So just quickly, I'm going to tell you a bit about the Pyramid Science Foundation. This is an entity I formed in 2019 as a Pennsylvania nonprofit corporation. And in 2020, it was designated as a 501c3 organization by the Internal Revenue Service. We were founded to conduct scientific research relating to the value of pyramids, to human, physical, and behavioral health, the environment, agriculture, materials science, and other affiliated areas of research. The Pyramid Science Foundation is actively pursuing partnerships, as I mentioned, with academics, fluid dynamics, CFD professionals, free energy entrepreneurs, harmonics experts, aircraft and nuclear fusion designers, and others who can see value in incorporating golden ratio scaling into their respective fields of endeavor. So if you have any questions about any of that as well, feel free to contact me at charlie@pyramidsciencefoundation.org or call me at 412-474-3481. For more information about the foundation, please feel free to go to our YouTube page, or excuse me, to our website, which is pyramidsciencefoundation.org. Also, you can go to our YouTube and Rumble pages with the Pyramid Science Foundation, and you're going to find over 350 research videos, interviews, and other items of interest relating to pyramid energy fields and golden ratio scaling. In the next half, the next part of this is just going to be the appendix, and I'll be back to introduce that in just a moment. The appendix to this documentary contains many, many more examples of GRS that's found in nature and in all types of aerodynamic designs for airplanes, missiles, rockets, and the like. So rather than boring some of you who don't want to see all of these in the front half, I've compiled them all in the back. There is a listing in the comments section that timestamps each of these different sections, but I will go over those with you real quickly. You can see here in part 7, the appendix, we're going to have additional examples of tornadoes, water vortexes, iron furnaces, maritime vessels, helicopters, private jets, commercial jets, supersonic aircraft, and missiles. So use the timestamp if you're interested in pursuing additional examples of any of these objects, and that should get you to the right place. So I'm going to put on some music while all of these play. I hope you enjoy it, and we'll be back at the end of the appendix.
got one.